Somewhere in the Milky Way, an invisible mass is bending starlight, stealing seconds from time and commanding the orbits of stars without ever being seen. Step closer and the universe stops behaving like a place and starts behaving like a limit. If you could fall all the way in, past the horizon, would you find a doorway to deeper reality or the edge of understanding itself? It is not a monster made of darkness, but a geometry with a measurable signature, precise as an orbit, ruthless as an equation. In the crowded heart of our galaxy, behind veils of dust, a hidden monarch keeps perfect time with the stars that circle it. We cannot see the ruler directly, yet its gravity writes a record in motion, in heat, and in ripples across spacetime. This film follows that record as far as nature allows. We will separate what is observed from what is inferred, what telescopes confirm, what mathematics predicts, and what physics forbids us to know. A black hole is not a hole in space. It is a region where out becomes a direction that no longer exists. The closer you approach, the universe grows unfamiliar. Light bends into rings, signals redden into silence, and seconds refuse to agree. From a safe distance, the story begins with numbers replacing metaphors. Stars near the galactic center swing through tight arcs, their spectra shifting as gravity accelerates them, and their paths tracing the mass of an object compact beyond ordinary matter. That evidence leads us to Sagittarius A, quiet in appearance, overwhelming in influence, an anchor point for our descent. Then the calm breaks. When a black hole feeds, the darkness turns incandescent as matter is forced to slow down, collide, and heat beyond imagination. Disks of plasma ignite in X-rays, magnetic fields twist into turbulence, and the last stable orbit becomes a cliff edge written into spacetime. In some systems, the infall does not end in silence. Spin and magnetic fury can drive jets, narrow spears of light that pierce galaxies and advertise the presence of an unseen engine. Yet the true threshold is not a surface, and not a place you can touch. The event horizon is a one-way boundary in causality, a line drawn by the behavior of light itself. To an observer far away, a falling clock seems to slow and fade, its messages stretched and drained of energy until they blend into the background. To the traveller, the crossing can be eerily ordinary, and then the map of possible futures changes, irrevocably. Beyond that boundary, we enter a region where our intuition fails first, and our definitions fail soon after. Inside, toward the centre, is not a choice but a requirement, and time begins to behave like a direction with only one way forward. We cannot send cameras there, and we cannot receive postcards back, but the universe provides another messenger. Gravitational waves, faint tremors from collisions that let us test the exterior with astonishing precision. And still, the central question remains, waiting in the dark. What do we actually know, through observation, theory, and hard limits of physics, about what happens as you approach a black hole, cross its horizon, and head toward its center as far as understanding allows? At the end of the trail lies a word that sounds like an answer, but is really a warning: singularity. It is the point where equations diverge, where prediction breaks, and where our best theories admit they are incomplete. So this journey is not only inward through space, but inward through the methods we trust. We will watch gravity weigh the unseen, watch light struggle near the brink, and listen to space-time ring like a struck bell after a merger. We will confront the unsettling possibility that what falls in may not be allowed to vanish from the universe's accounting, because quantum law insists that information cannot simply be destroyed. In the end, the center of a black hole is not merely a location, it is where relativity meets quantum mechanics, and neither agrees to yield, where cosmology learns that the deeper secrets may be written not in light, but in gravity, geometry, and information. And as we descend, one question will tighten its grip on every image we see. Are black holes the ultimate prisons of the universe, or the sharpest clues to how reality is built? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin with the darkness that has a shape, then follow the Milky Way's hidden monarch into fire, jets, horizons, and the limits of prediction. Step by step, we will go as far as evidence can carry us, and no farther. Black holes are not holes in the ordinary sense, not empty punctures you could fall through like a trapdoor. They are compact, measurable objects whose presence can be mapped by motion, light, and time. They do not shine, yet they power some of the brightest scenes in the universe, scenes so luminous they can outglare entire galaxies. They sit unseen, yet they steer stars, gas, and even whole galaxies, shaping cosmic architecture over billions of years. Call them invisible engines. Their fuel is gravity, and their exhaust is the energy released by matter that almost escapes. The paradox is simple and unsettling. Something we cannot see leaves fingerprints everywhere, and those fingerprints are precise. A star speeds up in a tight orbit, its spectral lines shifting as it swings toward and away from us. A disk of gas heats to millions of degrees, glowing in X-rays as ions and electrons collide in violent turbulence. A ripple crosses Earth, and detectors move less than an atom, yet the pattern matches a distant collision. These are not metaphors. They are measurements that let us infer a dark object with a specific mass and a specific size. To understand why, we start with a definition that sounds like a trick. A black hole is a region where escape velocity exceeds the speed of light. Escape velocity is the speed you would need to climb out forever, never falling back, even as gravity weakens with distance. For Earth, it is about 11 kilometers per second, and for the Sun, it is about 617 kilometers per second. But for a sufficiently compact mass, the number rises past light itself. If light cannot escape, neither can any signal that carries information outward. No radio pulse, no flash, no warning. That is why black holes look black, even when they are surrounded by fire. This definition is not just Newtonian intuition. It is the modern consequence of Einstein's general relativity, where gravity is space-time curvature rather than a force pulling across distance. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. In this view, a black hole is not a vacuum with a monster inside. It is a geometry so steep that all future paths tilt inward, like a landscape whose slopes point toward a place you cannot walk around. Historically, the idea arrived before the evidence did, and it arrived in stages. Einstein published General Relativity in 1915, and within months, Carl Schwarzschild found a solution describing a compact mass with a critical radius, even while serving on the Eastern Front. For decades, that radius looked like a mathematical oddity, and many physicists wondered whether nature would ever permit it. Only later, as radio astronomy and X-ray telescopes opened new windows, did the sky begin to supply objects that behaved exactly as the equations demanded. The boundary of that geometry has a name we will return to again and again. It is the event horizon. The event horizon is not a physical surface you could scrape or stand on, and it has no texture of its own. It is a one-way boundary in space-time, defined by what can still reach infinity. Outside it, light can climb away, though it may be bent and delayed, and its path can be twisted into arcs and rings. Inside it, every possible path forward leads deeper, even for light. That one-way rule matters because it sets the limit of observation. We can watch what happens near the horizon, but we cannot receive messages from beyond it. Even the word near becomes technical here, because gravity changes what distance and time mean. A meter measured by a local ruler is not the same as a meter inferred from far away, and the horizon marks where those comparisons become extreme. Yet black holes are not silent. Matter outside the horizon can glow, collide, and radiate before it disappears. Gas falling inward does not drop straight down like a stone. It usually forms an accretion disk, a rotating flow shaped by angular momentum, because most cosmic gas arrives with a sideways drift it cannot simply erase. As the disk spirals inward, it must shed angular momentum, and that transport is driven by friction-like processes. In real disks, the key agent is magnetic turbulence. Fields threading the plasma act like tangled springs, coupling layers that want to slide past each other. Friction and magnetic turbulence in that disk convert gravitational energy into heat. The result is light across the spectrum, often strongest in X-rays, where temperatures reach tens of millions of degrees and atoms are stripped to bare nuclei. Sometimes the disk does more than shine. It can launch narrow relativistic jets, collimated beams that punch through surrounding gas and broadcast the black hole's presence across intergalactic space. So the darkness has a shape, traced by the bright matter that circles it. The black hole is inferred by what the surrounding universe is forced to do. Still, we should be careful with the word see. We do not see the black hole itself, We see its influence on light and matter, and we test whether that influence matches a compact object with an event horizon. This documentary makes a promise and sets a boundary. We will travel inward using what we can truly test, and we will mark where testing ends. Our descent will be built from real data, not imagined interiors. We will use stellar orbits, gravitational waves, high-energy radiation, and horizon-scale images. Each tool answers a different question. Orbits weigh the central mass, because gravity sets the speed required to stay bound. X-rays reveal hot gas and magnetic fields, because energetic plasmas radiate in distinctive lines and continua. Gravitational waves map violent mergers, because spacetime itself carries the signature of accelerating mass, and images like those from the Event Horizon Telescope constrain the size of the shadow, the ring of light, and the geometry near the horizon. They do it by linking radio dishes across Earth into a single virtual telescope, using atomic clocks and careful calibration to preserve phase information. Together they turn a once speculative object into a measured one. They also expose how quickly certainty fades as we approach the centre, because the centre is where our equations become most extreme. In classical general relativity, the math points to a singularity. A singularity is not a place we can visit with a camera. It is a signal that curvature, density, or tidal forces diverge in the equations, meaning the numbers blow up rather than settling into finite predictions. That divergence is often read as a breakdown of the theory, not a confirmed feature of nature. It tells us that something is missing, and it tells us that our current map ends at a cliff. What is missing is a quantum description of gravity. We have quantum mechanics for particles and fields, and relativity for spacetime, but not a complete union. Black holes force that conflict into one object. They compress mass into a region where quantum effects should matter, while spacetime curvature becomes dominant, and those two demands pull our theories in opposite directions. So the journey has two tracks running in parallel. One track is what we can observe and calculate with confidence. The other is what the best theories suggest but cannot yet confirm. The event horizon sits between them like a line on a map. It is not the end of physics, but it is the end of direct communication. Crossing it changes what outside can ever know about inside. That is why black holes are not only astrophysical objects, but also philosophical traps, forcing us to ask what knowledge means when signals cannot return. They challenge our everyday sense of time. Near a black hole, time dilation becomes dramatic, because clocks follow different paths through curved spacetime, and gravity changes how those paths accumulate seconds. To a distant observer, processes near the horizon appear slowed and reddened as light loses energy climbing out of the gravitational well. To a falling observer, local time feels normal until tidal forces grow and the environment becomes impossible to ignore. They challenge our sense of space. Tidal gravity stretches and squeezes because the pull on your feet differs from the pull on your head, and that difference grows rapidly as you approach a compact mass. For small black holes, those tides can tear matter apart well before the horizon, shredding stars into long streams in a tidal disruption event. For supermassive black holes, the horizon can be crossed with gentler gradients, because the same mass is spread over a much larger radius. They also challenge our sense of information. If nothing escapes, what happens to the details of what falls in, and can the universe lose information? This is the black hole information problem, and it sits at the intersection of quantum theory, thermodynamics, and gravity. It also forces a practical question. If physics is reversible at the microscopic level, how can a horizon seem to erase a story forever? We will not solve it here, but we must name it early. It is one of the reasons black holes are laboratories for the deepest laws we have. Even the language we use carries tension. We say inside and outside, but the horizon is not a wall, and space-time itself is what is changing. We say center, but the center in the equations is not like the center of a planet. It is a limit where the known rules stop giving finite answers, and where prediction becomes more like a warning label. So the question becomes sharper. What do we actually know through observation and tested theory about approaching a black hole, crossing its horizon and heading inward? We know there is a mass, we know it is compact. We know it warps space-time in ways that match general relativity with stunning accuracy, even when tested with fast-moving stars and precise timing. We know that matter can orbit stably at certain distances, then becomes unstable closer in. We know there is an innermost region where circular orbits fail, a boundary that depends on spin and sets a natural edge for bright disk emission. We know that spinning black holes drag spacetime around them, an effect called frame dragging. We infer spin from disk behavior and from gravitational wave signals, because spin changes the orbital rhythm and the final ring down. We know that mergers ring like struck bells. The final object settles into a state described by mass and spin, matching the no-hair prediction so far as current detector sensitivity can tell. But we do not know what replaces the singularity, if anything does. We do not know how quantum information is encoded and released, if it is released at all. We do not know whether the horizon is always smooth for an infalling observer, or whether quantum effects could make it violent under some conditions. We do not know whether spacetime remains continuous at the smaller scales, or whether it becomes granular, emergent, or something stranger. The honest story is not that black holes are pure mystery. The honest story is that they are half-mapped territory and half-blank page, and the boundary between the two is where the most careful language matters. That is why they matter. They are where astronomy meets fundamental physics, and where the universe forces us to confront the limits of our models. They also matter because they are common. Stellar mass black holes are the remnants of massive stars left behind after supernovae or direct collapse when nuclear fuel is exhausted. Supermassive black holes sit in the cores of most galaxies, and their masses correlate with the properties of the surrounding stellar bulge. Their growth shapes their environments. Jets launched near the horizon can heat galactic gas and regulate star formation, preventing clouds from cooling into new stars too quickly. Accretion can light up quasars across cosmic time, turning distant galactic nuclei into beacons visible from the early universe. So when we ask what happens near a black hole, we're also asking how galaxies evolve. The smallest scales can control the larger structures, and the connection is written in feedback. Energy out, matter rearranged, history altered. Now we set the rules for our descent. We will treat every claim as a rung on a ladder, and we will label which rungs are solid. Solid rungs come from repeated observation and cross-checked models, where independent methods converge on the same mass, the same compactness, the same relativistic effects. Less solid rungs come from extrapolation into regimes we cannot yet probe, where equations are trusted but unverified. We will keep returning to one principle. If a statement cannot be tested even in principle, we will treat it as speculation, not conclusion. At the same time, we will not dismiss the power of theory. General relativity predicted black holes before we had strong evidence, and it predicted their signatures, from gravitational lensing to the timing of orbiting bodies. The goal is not to choose between imagination and measurement. The goal is to let measurement discipline imagination, and let imagination guide new measurements, because the best questions often arrive before the best instruments. So we begin at the scale where black holes stop being abstract. We begin where the Milky Way itself gives us a target. Somewhere in our galactic centre, stars orbit an unseen mass with a period of years. Their paths trace an object millions of times the Sun's mass, confined to a region smaller than our solar system. In infrared light, where dust becomes more transparent, those stars appear as sharp points weaving through a crowded field. Over time, their arcs close into ellipses, and one star in particular swings through its closest approach at a speed of thousands of kilometers per second. That object is quiet compared to a quasar, but it is close enough to study in detail. It is the nearest supermassive black hole candidate we have, known as Sagittarius A, a compact radio source buried behind tens of thousands of light-years of intervening stars and dust. If we want to meet a black hole with confidence, we start there. We start in our own backyard, where gravity writes its signature in starlight, and where decades of patient observation turn faint motion into a decisive mass. Next, we follow those stars as they race around the dark. We use their orbits to weigh the invisible and to draw the first hard outline of the darkness. From that outline, the descent becomes real. We begin where black holes stop being abstract and start becoming measurable, where numbers replace metaphors and gravity leaves a track. At the Milky Way's centre, behind thick dust lanes and crowded stars, a compact radio source marks the target. Astronomers call it Sagittarius A, or Sgya A-Yund, and it sits about 26,000 light-years away. It is quiet compared with quasars, yet it dominates the inner galaxy's gravity. In wide shots, the galactic bulge looks serene, yet the central parsecs are a packed, restless arena. SGRAR is not identified by a bright surface or a blazing disk, because there is no surface to see. It is identified by what nearby stars are forced to do over time, as if an invisible conductor sets their tempo. Their motion is the evidence, and decades of tracking turn motion into mass. This is the first major step toward the horizon, a black hole revealed not by light but by gravity, motion, and time. The galactic center is hidden in visible light, because interstellar dust grains scatter and absorb optical photons like smoke swallowing a flashlight beam. Infrared can cut through dust, because longer wavelengths slip between particles and lose less energy to absorption. With adaptive optics and long observing campaigns, individual stars can be followed night after night. The technique is almost surgical. Mirrors flex in real time to cancel atmospheric blur and sharpen the field. Their positions shift by tiny angles, yet the pattern is coherent and repeatable. The stars trace arcs that close into ellipses, and the ellipses point to the same focus. Even the scale of the measurement is part of the drama. From Earth, these stellar motions are measured in milliseconds, comparable to tracking a coin on the moon. Each data point is a time-stamped position, and each position becomes a constraint on the gravitational field. Over years, the sky itself becomes a graph, and the stars draw the curve. In Newton's language, bound orbits follow Kepler's laws when one mass dominates, and the ellipse is the natural shape of gravity's bookkeeping. In Einstein's language, those orbits are geodesics in curved spacetime, corrected by relativity when speeds and gravity become extreme. Either way, the key is that orbital period and orbital size are linked to central mass. If you can measure the orbit, you can weigh the unseen object. The math is old, but the setting is new. Kepler's rules applied at the edge of a relativistic abyss. The method is simple in principle and brutal in practice, because it demands patience measured in decades rather than nights. Measure a star's position on the sky over many years. Measure its radial velocity from Doppler shifts as it moves toward and away from us. Combine the three-dimensional motion with distance to the galactic center, and solve for the gravitational potential. Every uncertainty matters: distance, calibration, atmospheric distortion, and the subtle drift of reference stars. This effort did not appear overnight. In the 1990s and early 2000s, competing teams refined infrared imaging and spectroscopy until the central cluster became a laboratory. The work turned the galactic center from a blurred glow into a resolved swarm of named stars. In that swarm, one star became the decisive probe because it moves fast and returns quickly. It is called S2, and it completes an orbit in about 16 years, short enough that a human career can watch multiple passages. Near closest approach, it reaches thousands of kilometers per second, a few percent of light speed. At pericenter, it dives through the inner region like a comet whipped around the sun, except the sun is invisible. Its path swings around an empty point, as if orbiting a mass that refuses to glow. On a time-lapse, the star seems to hesitate, then accelerate, gravity tightening its grip as the arc steepens. From S2 and many other stars, the enclosed mass is about 4 million suns, a figure that has hardened as instruments improved. The uncertainty has shrunk as more orbits closed, more velocities were measured, and systematic errors were hunted down. The mass is concentrated inside a region comparable to the size of the solar system. That combination of huge mass and tiny volume is the core of the case. It is not merely heavy, it is compact in a way that ordinary matter struggles to imitate. A cluster of dark stars could, in principle, mimic the gravity for a while, but the phrase, "for a while," is doing the work. Pack millions of solar masses into a solar system-sized volume, and the cluster becomes a pressure cooker of encounters. Such a cluster would be unstable, colliding and evaporating on short timescales, and it would tend to collapse or disperse. It would also radiate and leave signatures that are not seen, because close interactions produce heat, light, and debris. The simplest consistent explanation is a single compact object. The argument does not rest on one orbit, but on a population, and that population gives the same answer from different angles. Dozens of stars in the central arc second follow Keplerian ellipses with a common focus. Their speeds rise as they approach that focus, exactly as gravity demands, and slow again as they climb away. The same mass emerges from independent fits, using different stars and different techniques. When many clocks agree, the hidden mass stops being a guess and becomes a measurement. As the data improved, the story moved beyond Newton. because precision began to expose small departures from perfect closure. S2 does not trace a perfect closed ellipse in the same plane forever. Its orbit precesses, with the point of closest approach rotating over time like a slowly turning arrow. That precession matches general relativity in the gravitational field of a compact mass. The effect is subtle, but it is also profound. Spacetime itself is shaping the orbit. Relativity also predicts a gravitational redshift and a transverse Doppler effect near pericenter, and together they change how the star's light arrives. When S2 is deepest in the potential well, its spectral lines shift beyond what classical motion alone predicts. Those shifts have been measured, and they agree with Einstein's equations within current precision. The center behaves like a relativistic object, not a diffuse cluster. In plain terms, the star's light is climbing out of a deeper gravitational pit, and it pays an energy toll. There is another subtle clue in the reference frame itself, and it speaks to the black hole's inertia. The black hole's gravity should be centered on a fixed point, not wandering with the stars like a lightweight object being tugged around. Radio interferometry pins Escure to a remarkably stationary position relative to the galaxy. Its proper motion is tiny, consistent with a massive object anchored at the dynamical center. The galaxy's heart is not drifting. It is the point around which everything else negotiates its orbit. We can now translate mass into a characteristic size even before we see anything like a horizon, because relativity gives mass a length scale. For a non-spinning black hole, the Schwarzschild radius is about 3 kilometers per solar mass. Multiply by 4 million, and the radius is roughly 12 million kilometers. That is the scale where escape velocity reaches light speed, and where outward becomes a direction that no longer guarantees return. The number is stark because it turns a cosmic monster into a boundary you can write in kilometers. 12 million kilometers sounds large until it is placed in astronomical units, the distances that define our everyday solar system intuition. 1 AU is about 150 million kilometers, the Earth-to-Sun distance. The Schwarzschild radius of Escure is about 0.08 AU. The event horizon diameter is about 0.16 AU, smaller than Mercury's orbit by a wide margin. If you could place it at the Sun, the horizon would fit well inside the inner planetary region, and the planets would still be far away. This is what event horizon size means in practice, and it is easy to misunderstand. It is not the size of the galaxy's influence, which extends for light years and shapes the orbits of stars in the bulge. It is the size of the one-way boundary in spacetime, measured in kilometers and in AU. The stars we track are far outside it, yet their motion still reveals it indirectly. Gravity's reach is vast, but the point of no return is surprisingly compact. The next question is, why Escure I is so dim for its mass? Because mass alone does not guarantee brilliance. A 4 million solar mass black hole could shine like a quasar if fed efficiently, converting gravitational energy into radiation. Instead, the galactic center is a low luminosity nucleus. The black hole is starving, or at least eating in a way that wastes little light. In visible images, the center looks like a crowded city, yet the central engine is more like a banked fire. Accretion at low rates behaves differently from a thin, bright disk, and the difference is rooted in how energy moves between particles. The gas can be hot, tenuous, and magnetized, forming a radiatively inefficient flow. Protons and electrons may not share energy quickly, leaving electrons cooler than the ions, and cooler electrons radiate less. Much of the energy can be carried inward rather than radiated outward, a kind of thermal cargo swallowed by the whole. The flow becomes a dim furnace whose heat is trapped and advected inward. Magnetic fields matter because the inflowing gas is a plasma, and plasma is never just fluid, it is charged matter tied to field lines. Turbulence and reconnection can heat particles and launch outflows, reshaping where the gas goes and how long it lingers. The flow can be thick and puffed up, not a neat pancake, and it can shed material in winds. In such a regime, the black hole can swallow energy along with matter. The result is counterintuitive. Less fuel can mean less light, even when gravity is strongest. Even a quiet black hole is not perfectly silent, and the galactic center occasionally flickers like an eye opening in the dark. Escure produces sporadic flares seen in infrared and X-rays. These flares rise and fade on timescales of minutes to hours, implying a compact emitting region. The variability points to activity close to the horizon scale, where orbital times are short. When brightness changes that fast, the source cannot be large. Light itself sets the maximum size. The leading picture is that the electrons are accelerated in magnetic reconnection events, where twisted field lines snap, rearrange, and dump energy into particles. They radiate synchrotron emission in infrared and radio, and can upscatter photons to X-ray energies through inverse Compton processes. The details are still debated because plasma physics near a horizon is messy and nonlinear. But the message is consistent. Something small and relativistic is stirring near the centre, and it is stirring in bursts. For years, the best evidence for the horizon scale was indirect, and the horizon remained a boundary inferred rather than seen. Then, a global instrument attempted the most difficult image in astronomy. The Event Horizon Telescope links radio dishes across Earth into a virtual planet-sized telescope. It observes at millimeter wavelengths that can penetrate the galactic center's scattering screen. The technique is interferometry. Signals are time-stamped with atomic clocks, then combined to synthesize a single enormous aperture. The challenge is not only resolution, but also clarity. Between us and the center lies turbulent ionized gas that blurs radio waves, like looking through rippling water. Millimeter wavelengths reduce that blurring, and careful calibration peels away instrumental noise. The data arrive as fragments, correlations between distant antennas, and the image must be reconstructed from those fragments. It is less like taking a photograph and more like solving a puzzle with missing pieces. In 2022, the EHT collaboration released an image of SGRA's emission region. The result is a bright ring with a darker center, consistent with strong gravitational lensing. The ring is not a photograph of the event horizon as a surface, because a horizon emits no light. It is light from hot plasma that has been bent around the black hole. On screen, the glow looks almost gentle, yet it is produced by matter moving at relativistic speeds in a magnetic storm. The ring's diameter matches what general relativity predicts for a 4 million solar mass black hole. The apparent size is larger than the horizon because light paths are curved and partially trapped. Photons can orbit briefly near the photon sphere before escaping, and that orbiting concentrates brightness into a ring. The image is a map of space-time geometry acting on emission. In effect, gravity is drawing its own signature by bending the light that tries to leave. It is also a reminder of what we cannot see, and why the language must be careful. The dark center is called the shadow, but it is not a hole punched in a glowing wall. It is the set of directions from which light cannot reach us because it falls inward. The horizon itself remains a boundary defined by causality, not by brightness. The shadow is the silhouette of lost paths, an absence created by geometry rather than by material darkness. SGR-A arc is harder to image than the black hole in M87 for a simple reason, and that reason is time. It is smaller in mass, so its characteristic timescales are minutes, not days. While the EHT observes, the source changes, and the image must be reconstructed from a moving target. The fact that a ring still emerges is part of the triumph. It suggests that, beneath the turbulence, the space-time lens is stable enough to imprint a persistent shape. Motion, gravity, and time now converge on the same object, and each line of evidence reinforces the others. Stellar orbits weigh it at 4 million suns. Compactness arguments confine that mass to a tiny region. Millimeter interferometry finds a ring of lensed emission at the expected scale. The simplest consistent interpretation is a supermassive black hole. The Milky Way's hidden monarch is no longer a theoretical placeholder. It is an observed gravitational center. Time enters the story in another way, and it points toward the deeper journey we are preparing to take. Near a massive compact object, clocks do not agree, even if they are built identically and synchronized far away. General relativity predicts gravitational time dilation, where time runs slower deeper in a potential well. It also predicts special relativistic time dilation from high orbital speeds. Together, they mean that now becomes a local statement rather than a universal one. For stars like S2, both effects become measurable near closest approach, where the star is both fast and deep in the gravitational field. The star's light carries the imprint of its motion and its depth in the gravitational field. Those imprints match the relativistic predictions, confirming that the galactic center is a strong gravity laboratory. The closer you get, the more time itself becomes part of the evidence. It raises a quiet question. If time stretches near the center, what does an infalling clock truly experience? This matters for our central question about approaching and crossing a horizon, because the horizon is not just a distance on a map. The horizon is a limit on communication and on shared time, a boundary where outward signals fail. Far away, we can define a stable clock and a stable coordinate grid. Near the black hole, those definitions stretch, and comparisons become observer-dependent. What looks like a slow approach from one vantage can be a swift plunge from another. SGRA lets us test the approach without crossing the line, and that is part of its value. We can watch matter orbit, flare, and disappear from view. We can measure precession and redshift and infer curvature. We can estimate the horizon size and compare it to the ring's scale. Each measurement tightens the narrative, turning the idea of a horizon into a quantitative target. Yet SGRA also shows the limits of a quiet black hole, because dim accretion hides the last moments of infall. Low accretion means less light to trace the final plunge. The flow is faint, turbulent, and intermittent, and it hides details in variability. Even when it flares, the emission is patchy, and the plasma does not behave like a simple, steady disk. If we want to understand how black holes feed, we need examples that announce themselves. This documentary makes a promise and sets a boundary, because the temptation to overinterpret is strongest near the edge of the unknown. We will keep separating what is measured from what is extrapolated, especially as we move inward. SGRA-SEN gives us a measured monarch, defined by orbits and by a horizon-scale ring. It also points to the next step, where feeding becomes impossible to ignore. The quiet center is a baseline, a control case for black holes that barely eat. If SGRF is quiet, other black holes are loud. Across the universe, some are surrounded by bright disks and launch jets that outshine their galaxies. Those beacons reveal how gravity converts infall into radiation, and how horizons shape the last stable paths. To go further toward the center, we follow the brightest feeders. Their light is not a distraction, it is a diagnostic, a tracer of matter, as it spirals toward the point of no return. We leave the Milky Way's hidden monarch with a clear conclusion, built from multiple methods that agree on the same invisible object. An invisible object can be weighed by the choreography of stars, its size can be bounded by the physics of escape and by horizon-scale imaging. Its gravity can be tested by relativistic shifts that treat time as an observable. In the darkness at the center, the evidence is not a single flash, but a long, consistent pattern. The descent is no longer philosophical because the measurements have pinned the monster to a mass, a size, and a geometry. The horizon has a scale, the mass has a number, and the curvature has a signature. From here, we move from a quiet ruler to the loud engines that teach us how black holes grow. The next chapter follows the light that almost escapes. SGRA taught us how to weigh a quiet black hole by gravity alone. Now we follow the cases where feeding turns darkness into a beacon. A black hole does not shine, yet infalling matter can radiate with brutal efficiency when it is forced to slow down. The energy source is not fusion or chemistry, and it is not a hidden furnace. It is gravitational potential energy, converted into heat and light as matter falls into deeper curvature. In the simplest picture, gravity accelerates gas inward, and compression raises its temperature as density climbs. But the real story is messier. Gas is a fluid, not a test particle, and it shocks, shears, and collides. Those chaotic interactions scramble organized motion into thermal motion, and temperature becomes a ledger of lost order. The closer the gas gets, the more energy each kilogram can release before it disappears from view. Around a black hole, down is not a direction, but a steepening gradient in spacetime itself. Every inward step deepens the gravitational well, and the cost of staying in orbit rises sharply. In the best conditions, accretion rivals the most efficient power plants in nature, and it does so without any nuclear reactions. A thin disk around a spinning black hole can convert an astonishing fraction of rest mass into radiation. That is why some black holes outshine their host galaxies, turning a central void into the brightest point for billions of light years. Visually, this is where darkness becomes architecture. A faint rotating haze condenses into a luminous ring, and the ring brightens toward its inner edge. The light is not coming from the hole, but from the traffic jam of matter trying to avoid it. The first step is understanding why matter rarely falls straight in, even when gravity seems irresistible. Most gas arrives with angular momentum inherited from orbital motion, stellar winds, or the tidal shredding of a passing cloud. Angular momentum resists direct collapse, and it forces matter to circle as it falls. Even a small sideways speed becomes decisive near a compact object. Conservation of angular momentum means that as radius shrinks, orbital velocity must rise. What begins as a gentle drift can become a relativistic sprint, and the infall is redirected into rotation. Rotation creates a disk because collisions damp vertical motion faster than orbital motion, and the flow settles into a plane. Particles crossing the midplane collide, radiate, and lose the energy that kept them puffed up. The disk is not a solid object, but a shearing river of plasma whose neighbouring layers slide past one another. From above, the disk can look serene, like a vinyl record around a black centre. From within, it is violent. Eddies, shocks, and magnetic knots churn through a fluid that is often hotter than any laboratory plasma. The smoothness is an illusion created by distance and time averaging. A disk can only feed the black hole if it can lose angular momentum, and that requirement is the central engineering problem of accretion. Outer rings must gain angular momentum so inner rings can drop inward, and the exchange must be continuous. Without that transport, matter would orbit indefinitely, glowing faintly and never crossing the final threshold. This is where early theory met a wall. In the mid-20th century, models invoked viscosity as a stand-in for unknown microphysics, using a parameter to represent effective friction. Real disks are too thin and too hot for ordinary molecular friction to matter, because particles rarely collide like molecules in air. The effective viscosity comes from collective behaviour, turbulence and magnetic stresses that couple distant layers. The breakthrough came from recognising that ionised gas is tied to magnetic fields. In a plasma, charged particles spiral around field lines, and the field can act like a tensioned thread. That thread can transmit forces across the disk, even when particle collisions are too rare to do the job. The key driver is magnetorotational instability, or MRI, and it is deceptively simple in concept. A weak magnetic field links neighbouring rings like a spring between masses on different orbits. Differential rotation stretches that field, and the spring pulls back in a way that destabilises the flow. The inner ring orbits faster, so it tugs the field forward and loses angular momentum, drifting inward. The outer ring is pulled ahead, gains angular momentum and drifts outward. The separation grows, the field stretches more, and the instability feeds on the disk's shear. MRI turns smooth rotation into a churning magnetised flow that transports angular momentum outward while letting mass move inward. It also dissipates energy as heat, keeping the disk luminous rather than silent. In simulations, MRI is the engine that makes accretion possible, and it does so with only a modest seed field. This is where the documentary's promise matters, because we cannot watch individual field lines near a horizon. We cannot place probes inside the disk, and we cannot slow the flow for inspection. We can test the consequences through spectra, timing, and the shapes of emission that originate close to the black hole. As the disk heats, it radiates across the electromagnetic spectrum, and the peak depends strongly on mass. Cooler outer regions glow in optical and ultraviolet for supermassive black holes, where the disk is physically enormous. Hotter inner regions can reach millions of degrees and shine in X-rays, especially around stellar mass black holes. A useful intuition comes from blackbody radiation, even though real disks are more complex. Hotter material emits at shorter wavelengths, so the inner disk shifts toward X-rays as temperature climbs. The disk becomes a layered gradient, cooler, redder light farther out, and harder, bluer light closer in. The inner disk is where gravity is steepest and orbital speeds are highest, and the plasma becomes fully ionized. There, atoms are stripped into nuclei and electrons, and collisions are energetic enough to generate high-energy photons. X-rays become the most direct tracer of the last stable orbits, because they arise where the action is fastest. X-ray spectra carry fingerprints that let us map conditions we cannot resolve as images, and those fingerprints have a history. When X-ray astronomy matured in the late 20th century, satellites began to reveal broad features that did not match simple thermal emission. Those puzzling shapes became evidence that strong gravity was sculpting the light. One of the most important fingerprints is the iron K-alpha line, produced when iron atoms are excited and then emit a characteristic photon energy. Iron matters because it is abundant enough to be visible, and its atomic transitions sit in the X-ray band. In a disk irradiated by hard X-rays, iron can fluoresce like a cosmic neon sign. Near a black hole, that line is no longer narrow and symmetric, because the emitter is moving at a substantial fraction of light speed. Rapid orbital motion Doppler shifts the emission, boosting the approaching side and dimming the receding side. Strong gravity redshifts photons as they climb outward, draining energy from the light itself. The result is a broadened, skewed line profile shaped by relativity, and its asymmetry is the clue. A long red wing can extend to lower energies than any Newtonian disk would allow. That wing encodes how deep in the potential well the photons were born, and how hard spacetime made them climb. The line also carries another subtle signature: light bending. Near the black hole, photon paths curve, and regions of the disk can be magnified or hidden depending on geometry. What we observe is not just emission, but emission filtered through the lens of curved spacetime. In the same region, the disk can be covered by a hot corona of energetic electrons, tenuously hovering above the surface. The corona-Compton scatters softer photons up to X-ray energies, producing a hard continuum that can dominate the spectrum. It is a kind of high-energy fog, thin in density but powerful in effect. Some of that hard radiation reflects off the disk and imprints additional features, like a signature stamped onto the returning light. Reflection adds an iron line and a Compton hump that together act like an echo of illumination. The disk becomes both a lamp and a mirror, and the spectrum records both roles. Timing turns that mirror into a ruler. The delay between direct coronal light and reflected disk light can be measured in milliseconds for stellar mass systems, and in hours or days for AGN. In favourable systems, reverberation maps the inner flow as it flickers, converting time lags into distances measured in light seconds. These tools answer a specific part of our central question, and they do it without ever seeing the horizon directly. They tell us what happens as matter approaches the point where stable motion fails and where the disk's brightness is still strong. They also reveal where our inferences depend on models of plasma, geometry, and the changing shape of the corona. The disk does not extend inward forever as a stable carousel, because general relativity imposes a boundary. That boundary is the innermost stable circular orbit, the ISCO, and it is a mathematical feature with physical consequences. The ISCO is the last radius where a small perturbation does not trigger a plunge. Outside the ISCO, circular orbits can be stable and long-lived, and the disk can behave like a slowly draining reservoir. Inside it, circular motion becomes unstable, and matter cannot remain on a steady track even if it is still moving sideways. The ISCO is not the event horizon, but it is a practical edge for bright disk emission. This distinction matters for visuals because the horizon is not a glowing surface. The disk's inner edge is where brightness often peaks, and then drops as the plunge begins. If we could hover above the disk, we would see a bright, tight ring, and then a dimming region where trajectories stop looking like circles. The ISCO depends on black hole spin, and spin changes the story in a deeply relativistic way. For a non-spinning black hole, the ISCO lies at a fixed multiple of the gravitational radius, setting a predictable inner boundary. For a rapidly spinning black hole, prograde orbits can remain stable much closer in, tightening the luminous ring. Spin drags spacetime itself, an effect called frame dragging, and it alters what stationary even means near the hole. The orbital energy and angular momentum required to stay circular change with spin direction. That changes how much gravitational energy can be released before the plunge, and therefore how bright accretion can become. In observations, a smaller inferred ISCO often implies higher spin, although the inference is never purely geometric. It depends on assumptions about disk thickness, ionization, and how far inward stress persists. The measurement is powerful, but it is also a reminder that nature rarely offers clean laboratory conditions. This is why the phrase last safe orbit is more than drama, even if it sounds like fiction. It marks where the disk's slow spiral becomes a rapid fall, and where stability becomes a knife edge. It is the boundary between a luminous orbiting structure and a region where outward recovery is no longer possible. Approaching the ISCO, orbital periods shorten, and velocities approach a significant fraction of light speed, tightening the rhythm of the system. Doppler beaming intensifies, so the approaching side brightens like a headlight. Gravitational redshift deepens, and the spectrum shifts as if the disk is sinking into a darker colour. At these radii, time itself becomes part of the signal. Variability can be tied to orbital motion, and the fastest flickers hint at the smallest scales. When we see a rapid change in X-rays, we are watching physics unfold near the limit of stable motion. Then the character of the journey changes, and the disk's orderly spiral loses its last foothold. Once matter crosses the ISCO, it enters a plunge region, and the inward drift accelerates. It still has angular momentum, but not enough for a stable circle, and the geometry offers no gentle compromise. In the plunge, the inflow accelerates inward on roughly an orbital timescale, and that timescale can be startlingly short. There is no stable path outward that can be regained by small adjustments, because stability itself has ended. The flow becomes a one-way descent even before the horizon is crossed. This is a crucial limit for what we can know observationally, because the plunge region is fast and dim compared to the disk. Photons emitted there are more strongly redshifted and more easily captured by the black hole's gravity. Even when light escapes, it often escapes weakened, arriving as a whisper from a region that is quickly emptied. We can still model the plunge using general relativity and magnetohydrodynamics, and those models have become increasingly sophisticated. We can estimate how stress behaves near the ISCO and how magnetic fields thread the flow as it accelerates. But the data are indirect, and the uncertainties grow as we approach the horizon, where fewer photons return. Different black holes let us test these ideas on different scales, and scale is one of the universe's great teaching tools. Stellar mass black holes in X-ray binaries are a few to tens of solar masses, and their disks are compact. Their inner regions are hotter, and they radiate strongly in X-rays, making them bright targets for timing studies. In an X-ray binary, a black hole feeds from a companion star through winds or Roche lobe overflow, and the geometry can be dramatic. Gas can stream through an inner Lagrange point like water through a saddle, forming a disk that brightens as it tightens. Accretion rates can change quickly, and the source can switch states, as if the engine is changing gears. Those state changes are not just brightness changes, but spectral reorganizations. The disk can appear cooler and more dominant in one state, and the corona can harden the spectrum in another. Timing features like quasi-periodic oscillations track changes in the inner flow, hinting at shifting radii and changing magnetic structure. Because the mass is small, the characteristic timescales are short, and the inner disk can evolve in real time. Variability can occur in milliseconds to seconds, fast enough to feel like a heartbeat. That makes X-ray binaries laboratories for rapid accretion physics, where cause and effect can be traced with precision. Supermassive black holes in active galactic nuclei are millions to billions of solar masses, and their disks are vast by comparison. Their temperatures are cooler, often peaking in ultraviolet, and the optical emission can come from radii far larger than any stellar system. Their variability is slower, but their total power can be enormous, and their influence can reach across a galaxy. AGN can sustain bright accretion for long periods, shaping their host galaxies through radiation and outflows that heat and push surrounding gas. Quasars are AGN seen at high luminosity, visible across cosmic time as beacons from the early universe. They reveal how black holes grew with the universe, and how feeding could be common when galaxies were young. Historically, this realization changed astronomy's map of the cosmos. Quasars were first identified as star-like points with strange spectra, and their distances implied impossible luminosities. Accretion onto supermassive black holes provided the missing engine, turning an observational mystery into a physical narrative. The same physics scales with mass, but the observational emphasis changes with the clock rate of gravity. In stellar mass systems, we watch fast timing and hard X-ray spectra, and we can track transitions over days. In AGN, we combine multi-wavelength spectra, long-term variability, and reverberation delays that unfold over months or years. Across both classes, the central idea holds, and it is almost austere in its logic. Accretion converts gravity into radiation by forcing matter to shed angular momentum, and that shedding is the price of descent. The disk is the visible machinery, and the horizon is the hidden sink, swallowing whatever the disk cannot radiate away. The tension in this chapter is not only that matter is falling, but that matter is losing options as it approaches the center. Far out, it can orbit, collide, and radiate while remaining in the universe, still able to wander. Closer in, the geometry and the energy budget narrow the possibilities, and the rules become less forgiving. Stable orbits end at the ISCO, and the plunge begins, and that boundary is where our language turns sharp. From that point, the story becomes less like a spiral staircase and more like a drop, and the disk's bright order gives way to a brief dim rush. What does it mean to watch matter approach a point of no return, when the return is defined by light itself? This is where we connect back to the documentary's central question, and we do it with the tools that light allows. We can observe the approach through photons that almost escape, carrying Doppler shifts and gravitational redshifts like stamps in a passport. We can infer the last stable orbit through spectral distortions and timing echoes, and we can compare those inferences across many systems. But crossing the horizon itself remains a limit on direct knowledge, because the horizon is defined by the failure of signals to return. The disk's brightest regions lie outside that boundary, and the plunge region is brief and faint. The horizon is still defined by what cannot come back, and by the silence that follows. Even so, Accretion teaches us something essential about that boundary, and it teaches it repeatedly across the sky. It shows that black holes are not merely dark and not merely destructive. They are engines whose visible output is powered by the act of nearly falling in, by matter converting its altitude in gravity into light. Accretion also sets the stage for the next escalation, because magnetic fields do not only stir turbulence in disks. Under the right conditions, they organize into large-scale structures that can channel energy outward. The same fields that act like springs in MRI can, when ordered, become cables that connect the inner flow to distant space. Some black holes do not just eat, and the difference is visible across intergalactic distances. They fire narrow relativistic beams that pierce their surroundings and carry energy far beyond the disk, carving channels through gas. Those jets are not powered by a surface, because there is no surface, and they are not powered by nuclear fuel. They are powered by gravity, rotation, and magnetic fields, and by the disciplined geometry that fields can impose on plasma. The disk feeds the center twists the field, and the field guides energy outward, an inversion of the usual expectation that everything must fall in. When we see jets, we are seeing the black hole's environment choose a direction. So we end this chapter at the inner edge of the disk, where the last safe orbit gives way. Matter plunges inward, and light struggles to escape, and the final photons are stretched and weakened as they climb. Above the disk, magnetic fields tighten and point outward, as if the system is preparing to exhale. Next, we follow those fields as they thread the horizon's neighborhood. We follow how feeding can turn into launching, and how black holes can reshape galaxies with jets. The void is not only a destination, it is a machine with outputs we can measure, right up to the edge of silence. Accretion taught us how matter falls inward and radiates before the final plunge. Jets teach the opposite lesson. Some black holes launch narrow beams that escape, staying bright across intergalactic space. On screen, the contrast is almost unfair. The disk glows like a hot spinning ember, while a thin line of light spears outward, straight, stubborn, and impossibly long. A relativistic jet is a collimated outflow of plasma and electromagnetic energy. It rises from the inner disk and the black hole's immediate neighborhood, where gravity is strongest and magnetic fields are most intensely wound. The plasma is not a simple gas. It is ionized matter, electrons and ions sometimes mixed with electron-positron pairs, so it responds instantly to electromagnetic forces, even while it rides the curvature of spacetime. The jet accelerates to near light speed and holds its shape for thousands of years. That persistence is a clue, because turbulence should shred a careless outflow, yet many jets remain narrow across scales that dwarf their host galaxies. Jets are not rare curiosities. They appear in stellar mass binaries in our galaxy and in active galactic nuclei, and they also appear in tidal disruption events when a star is torn apart. In a microquasar, the central black hole may be only a few solar masses, yet the physics scales up with mass in surprisingly elegant ways. Timescales stretch, sizes expand, and the same basic engine can operate from seconds to millions of years. We know jets exist because they announce themselves across the spectrum. Radio maps show long lobes and thin cores powered by synchrotron emission, the telltale glow of relativistic electrons spiraling around magnetic field lines. In radio images, the jet often looks like a filament drawn with a steady hand. Far from the core, it blossoms into lobes, ghostly balloons of magnetized plasma that mark where the beam has been working on its environment. Optical and X-ray images show knots and shocks where the beam slams into surrounding gas. Those bright beads are not decorations, they are places where energy is dissipated, particles are reaccelerated, and the flow briefly reveals its internal structure. At the highest energies, jets reach gamma rays. Rapid flares imply compact regions and extreme particle acceleration, because light cannot vary faster than the size of the emitting zone allows. When a blazer doubles in brightness in minutes, the implication is stark. Something near the launch region is converting electromagnetic energy into particle energy, with ruthless efficiency, under conditions we cannot reproduce on Earth. Polarization traces ordered magnetic fields that keep the flow disciplined. In practice, it is a kind of compass, an imprint of field geometry carried by photons that have travelled millions or billions of years. The geometry is the first clue. Jets are narrow, persistent, and aligned with the system's rotation axis, and that alignment points back to angular momentum and to magnetic fields anchored in the inner flow. A black hole is defined by mass, spin, and charge in general relativity. Charge is usually negligible in astrophysics because plasmas neutralize quickly, leaving mass and spin as the parameters that matter for real black holes. This no-hair simplicity is part of the unease. The object at the center is mathematically spare, yet the structures around it, disks, winds, and jets, can be among the most elaborate phenomena in the universe. Spin is not a decorative detail. It changes the space-time geometry outside the horizon, it changes the location of the innermost stable orbit, and it changes the efficiency of accretion. For a non-spinning black hole, stable circular orbits end farther out. For a rapidly spinning one, the inner edge can move inward, letting matter fall deeper before plunging, so more gravitational energy can be radiated or redirected. Spin also changes what the surrounding plasma can do with magnetic fields. In the inner regions, magnetic field lines can be stretched, twisted, and amplified because differential rotation and shear act like a cosmic dynamo. The rotating solution is the Kerr black hole. In Kerr geometry, space-time is not only curved, it is dragged around by the rotating mass so the local inertial frames are twisted. Frame dragging is not a metaphor. It is a measurable effect predicted by general relativity and tested around Earth. And near a black hole, the same effect becomes dominant and reshapes orbital motion. Visually, imagine a whirlpool in a dark ocean. The water is space-time itself, and anything that tries to hover, gas, photons, even magnetic fields tied to plasma, feels the swirl and is compelled to join the rotation. In a Kerr space-time, there is a region outside the event horizon where no observer can remain stationary. This is the ergosphere, and inside it all world lines are forced to co-rotate with the black hole's spin. The ergosphere is not the horizon. You can still escape from the ergosphere if you move outward fast enough, while the horizon is the true one-way boundary where outward-directed light cannot reach infinity. That boundary is not a physical surface you could scrape with a probe. It is a causal edge, an accounting rule written into space-time, where outward stops being a path that leads back to the universe. This distinction matters because energy extraction becomes possible in the ergosphere. The geometry allows negative energy orbits relative to distant observers, and that strange bookkeeping makes it possible, in principle, to reduce the black hole's rotational energy. The classic thought experiment is the Penrose process. A particle enters the ergosphere and splits. One fragment falls in with negative energy, and the other escapes with more energy than it arrived with. Historically, this was a turning point. It suggested that black holes are not only sinks. Under the right conditions, they can act like reservoirs of rotational energy that the outside universe can, at least in principle, draw down. Astrophysical jets are not powered by carefully arranged particle splits. They are powered by magnetic fields and plasma dynamics, yet the key idea remains the same. Rotation can be tapped and converted into outward energy flow. The leading mechanism is Blandford-Znajek, a spinning black hole threaded by large-scale magnetic flux acts like a unipolar inductor, and frame-dragging twists the field lines and drives electromagnetic currents that carry energy outward. In this picture, the jet is an electromagnetic structure first. Plasma is loaded onto the field and accelerated along it, and the jet becomes a channel where pointing flux converts into particle kinetic energy farther out. That conversion is not guaranteed to be smooth. Instabilities, reconnection, and shocks can act like valves, releasing energy in bursts, so the jet can flicker and flare even while its overall direction remains steady. The disk still matters because it supplies magnetic flux and plasma, The disk can also launch winds that help collimate the jet, shaping it like a nozzle shapes a flame. But the deepest power source can be the black hole's spin itself. The paradox is what makes jets feel like a spear of light from a dark center, an object defined by silence surrounded by a machine that roars. A horizon emits nothing, yet the space-time around it can organize fields and extract rotational energy, producing structures larger than galaxies and lasting longer than human civilization has existed. We see the scale most clearly in radio galaxies. Jets inflate lobes that extend hundreds of thousands of light years, and those lobes store energy in relativistic particles and magnetic fields long after the central engine varies. In deep radio surveys, the lobes look like faint symmetrical wings. They are the long memory of the system, archaeological layers of activity that let us infer how long the jet has been running. One of the cleanest examples is M87. Its central black hole is billions of solar masses, and its jet is visible from radio through X-rays, remaining collimated across enormous distances. In optical images, the jet is a pale, segmented ribbon. In X-rays, the same structure becomes sharper and more violent, as if the beam is revealing where it is hottest and where particles are being pushed hardest. The Event Horizon Telescope imaged M87 and revealed a ring of lensed emission near the horizon scale. That image anchored the jet to a measured central mass and a compact emission region, tying the largest structures to the smallest resolvable scales. It also changed the emotional geometry of the story. The jet was no longer an abstract line pointing to an unseen center. It was connected to a resolved shadow, a gravitational silhouette cast by curved space-time. M87's jet provides a laboratory for collimation and acceleration. Close to the core, the jet appears wide and then narrows, and farther out, bright knots mark shocks and instabilities in a flow that remains relativistic. Those knots are like mile markers on a highway of plasma. They hint at where the jet recollimates, where it overexpands and pinches back, and where magnetic energy may be reorganizing itself. Other systems show jets aimed almost directly at us. These are blasters, and relativistic beaming makes them appear brighter and more variable because the jet's light is Doppler boosted into our line of sight. Blazers teach us about speed and orientation. Apparent superluminal motion appears in radio maps when a near light speed jet points toward us, and the effect is geometry and light travel time. Not true faster than light travel. The illusion works like this. Each new bright feature in the jet emits light from a slightly different position, and because the feature is chasing its own photons, the arrival times compress, so motion looks faster than it is. The same beaming explains extreme variability. A flare that would look modest from the side can look explosive head-on, which is one reason jets dominate gamma-ray catalogues. When we watch a blazer flicker, we are watching a relativistic searchlight. The beam is not sweeping across space like a lighthouse, but our alignment makes every internal change feel amplified. Jets also come in quieter forms. Many galaxies host radio jets that are weaker but still influential, and even when the nucleus is not a quasar, the jet can heat surrounding gas and prevent it from cooling. This is feedback, and it links black holes to galaxy evolution. Jets deposit energy into the interstellar and intracluster medium, stirring cavities and bubbles that show up as dark holes in X-ray maps of hot gas. They can suppress star formation by keeping gas hot and turbulent. They can also trigger star formation by compressing clouds in shocks, raising a question that echoes through astrophysics. When does violence create, and when does it sterilize? Feedback solves a puzzle that appears in cosmological simulations. Without a heating source, massive galaxies form too many stars too quickly, and jets provide a mechanism that regulates growth, connecting a horizon-scale engine to a galaxy-scale outcome. The implication is unsettling and beautiful. A region smaller than our solar system can influence the fate of a galaxy tens of thousands of light years wide, simply by controlling how gas cools and collapses. To understand why jets are narrow, we return to magnetic fields. A tangled field drives turbulence and heating in disks, while a coherent poloidal field can act like rails, guiding plasma outward and resisting sideways expansion. Collimation can come from hoop stresses in a toroidal field, where wrapped field lines pinch inward like a tightened belt. It can also come from external pressure in a disk wind or surrounding gas, and real jets likely use both. As distance increases, the balance can change. Near the base, electromagnetic stresses dominate, while farther out the jet negotiates with its environment, bending, flaring, or staying straight depending on what it plows through. The inner engine depends on how much magnetic flux reaches the black hole. Simulations show a regime called a magnetically arrested disk, where magnetic pressure becomes strong enough to choke inflow intermittently while powering strong jets. In that state, the disk is not a smooth river. It is a crowded intersection. Gas tries to fall inward, magnetic fields push back, and the system settles into a restless compromise that can produce powerful, sustained outflows. These ideas are tested indirectly through timing, spectra, and polarization. X-ray binaries show state changes where jets turn on and off with accretion geometry, while active galaxies show correlations between radio power and accretion indicators. The scatter is not a failure of the idea. Orientation, environment, and intermittency all blur the picture, so the same engine can look different depending on whether we view it from the side, from above, or through dense surrounding gas. Polarization is especially revealing because it traces magnetic order. In some sources, polarization swings during flares, implying changing field geometry near the launch region, while in others, stable polarization implies a persistent large-scale field. Those swings can be read like handwriting. A sudden rotation suggests a reorganizing magnetic structure, perhaps reconnection, while a steady angle suggests a long-lived field that remains anchored in the inner flow. Spin enters again through observations that hint at frame dragging. In tilted disks, lens, Thirring precession can twist the inner flow, modulating X-ray emission and producing quasi-periodic oscillations in stellar mass systems. Lens, Thirring precession is the orbital consequence of frame dragging. The black hole's spin axis defines a preferred direction in spacetime, and orbits that are not aligned can precess like a spinning top under gravity. In accretion flows, this can warp the disk. Viscosity and magnetic stresses can align the inner disk with the black hole's equator, an effect often called Bardeen-Peterson alignment, while the outer disk may keep its original tilt. The transition radius depends on disk thickness and internal stresses. If the disk is puffed up and hot, alignment may be weaker, while a thinner disk can communicate torques more effectively and settle into the black hole's equatorial plane. Observationally, warps and precession can appear as changing jet directions. Some radio galaxies show S-shaped jets that suggest slow reorientation, and some systems show multiple lobe pairs that hint at episodic activity with changing axes. Each bent jet invites a careful question. Is the engine precessing? Is the surrounding gas pushing the beam? Or is the black hole's spin axis itself changing through mergers and misaligned accretion? None of these clues is a direct gyroscope placed near the horizon. They are patterns that must be interpreted through models, and the documentary's rule still applies. We separate robust signatures from plausible but uncertain inference. Even so, the convergence is striking. Jets align with rotation axes, jet power correlates with magnetic flux and likely with spin, and frame dragging offers a natural way to twist fields and drive currents in the deepest gravitational region. This brings us back to the central question. What do we actually know as we approach a black hole, and what can we infer without pretending we have seen the unseen? Jets are part of the answer because they are observable consequences of near-horizon physics. They tell us that the neighbourhood of the horizon is not passive, but a region where gravity, rotation and electromagnetism couple strongly. It is a place where space-time geometry can do work on fields, and fields can do work on plasma. In plain terms, the shape of space-time helps organise a machine that can throw energy outward. Jets also sharpen the distinction between the horizon and the ergosphere. The horizon is the boundary of no return for matter and light, while the ergosphere is the boundary of no rest, where rotation forces motion and makes energy extraction possible. In a non-spinning Schwarzschild black hole, there is no ergosphere and no frame dragging. Accretion can still radiate and winds can still blow, but the most powerful persistent jets appear easiest to explain when spin and magnetic flux are both high. This is why Kerr black holes matter for our descent. Rotation changes the map of spacetime outside the horizon, adding a new kind of inevitability, where even the concept of standing still fails. As we follow the jet outward, we also learn what it cannot tell us. A jet is launched outside the horizon, so it carries information about the region near the boundary, not about what lies beyond it. The jet is a messenger from the last accessible zone. It is powered by what the universe can still communicate outward, and it is a reminder that our knowledge is bounded by causal structure, not by engineering ambition. Yet jets tempt us to imagine the centre as an engine room with moving parts. The truth is subtler, because the black hole itself is described by a few parameters: while the surrounding plasma supplies complexity and improvisation. The drama comes from their coupling in curved space-time. Gravity sets the stage and bends the paths, while magnetized matter provides the sparks, the currents, and the luminous signatures we can actually record. We can measure jet speeds, powers, and orientations. We can map radio lobes and date their expansion, and we can track polarization to infer magnetic order and compare these measurements across populations and across cosmic time. We can also measure spin indirectly through disk spectra and reflection features, and through gravitational wave ring-downs in merging black holes. Each method has systematics, but together they suggest that many black holes spin rapidly, especially those that grew through coherent accretion. Spin is stored energy. For a maximally spinning Kerr black hole, a significant fraction of its mass energy is in rotation, and Blandford, Znajek offers a way to tap that reservoir without violating the horizon's silence. The deeper mystery is that rotation changes what spacetime is doing. Frame dragging is not a force in the Newtonian sense. It is geometry telling inertial frames how to orient and telling magnetic fields how to twist. As we descend in this series, we keep narrowing the region where predictions are clean. Outside the disk, plasma physics complicates the picture, but does not erase gravity's imprint. While closer to the horizon, gravity dominates the causal structure. Even when the plasma remains turbulent, the boundary conditions tighten. Paths converge, timescales compress, and the difference between can escape and cannot escape becomes the most important distinction in the story. Jets therefore serve as a bridge chapter. They connect the luminous disk to the invisible boundary. They introduce spin as a defining property, and they show how rotation can shape everything we can still observe. They also set up the next step in the journey, where the boundary itself becomes the main character. If space-time can be twisted and mined for energy outside the horizon, what happens at the horizon? What does it mean, physically, to cross a one-way surface in time, and how would an observer describe that crossing while the rest of the universe watches from afar? To understand the center, we must face the boundary itself. The next chapter turns from the spear of light to the edge of silence. We ask what an event horizon is in practice, and what crossing it can ever mean to an observer. We have followed disks that glow and jets that escape, powered near the edge of silence. Now the story narrows to the boundary itself, where gravity stops being scenery and becomes fate. The central question sharpens here, because the horizon forces a distinction between what is difficult and what is forbidden. What do we actually know as we approach a horizon, and what is blocked by physics, not by technology? An event horizon is not a surface you can touch, scrape, or photograph like a mountain ridge. It is a causal boundary in space-time, defined by which futures remain connected to the outside universe. In Einstein's language, the horizon is drawn by light cones. Those invisible diagrams that separate can still communicate from can never communicate. If even light cannot climb back out, then no slower signal, no engine burn, and no clever maneuver can do better. Far from the black hole, space looks nearly flat and time feels ordinary, so intuition stays mostly intact. Close in, the geometry steepens, and the meaning of later depends on who is watching and how they keep time. The mathematics that first made this boundary explicit goes back more than a century to Schwarzschild's 1916 solution. At first, the horizon looked like a singularity in the equations, as if the theory itself broke there. Later, better coordinates revealed the truth. What broke was the map, not the territory. We need two viewpoints, because black holes split experience from appearance in a particularly unforgiving way. One observer stays far away, using distant clocks and telescopes, and another falls inward, carrying their own clock and their own sense of now. From far away, the infalling traveller never quite seems to arrive at the horizon, even if the traveller insists they do. The traveller's signals take longer to reach the outside, and each signal arrives more stretched than the last. Imagine the camera view from a distant station. A small beacon descends through a star field, its pulses still regular at first. Then the intervals widen, the colour warms, and the light thins, until the beacon becomes a slow, reddened whisper. This is gravitational time dilation seen from a distance, and it is not a mere metaphor about slowing down. Near the horizon, the traveller's clock runs slower relative to the far observer's clock, so the outside world assigns longer and longer times to the approach. In practical terms, the far observer's coordinate time behaves badly near the horizon because it stretches without limit. The outside can label events with a clock that never sees a final tick at the crossing, even though the traveller's own clock remains perfectly well behaved. The effect is not just about clocks, because light itself carries the bookkeeping of energy and time. It is also about photons losing energy as they climb out of the gravitational well, and that energy loss is seen as gravitational redshift. Each photon sent upward is drained by curvature, like a ball rolling uphill and surrendering kinetic energy. Its wavelength lengthens, its frequency drops, and its colour slides toward red, then infrared, then radio. For the distant observer, the traveller's beacon does not simply dim as if a lamp were turned down. It dims because each photon arrives with less energy, and because fewer photons arrive per unit of distant time. Those two factors multiply, and the fading becomes dramatic even before the traveller reaches the horizon. Signals are delayed, weakened, and spread out in time until they blend into background noise and the restless glow of the accretion flow. The freezing at the horizon is therefore an optical and causal illusion, created by redshift and light travel time. It is not a physical traffic jam at a wall, and it is not a crust that matter piles up upon. If we could amplify the signal without limit, we would still face the same structure of causality. The pulses would keep arriving later, and later, and later, each one more stretched, because the geometry dictates the delay. The traveller's perspective is different, and it is the first major shock of the descent into strong gravity. In classical general relativity, the traveller can cross the horizon in finite proper time, and that proper time is what their body and instruments actually register. Their wristwatch ticks normally, and local physics behaves as usual, at least for a sufficiently large black hole. A small laboratory falling freely cannot detect the horizon by any special local experiment, because the laws of physics in free fall mimic those of empty space. This is the equivalence principle at work, stated plainly. Free fall erases the feeling of gravity locally. You can be deep in a gravitational field and still feel weightless, even while the global geometry is doing something extreme. So how can both stories be true, when one says never arrives, and the other says crosses on schedule? The answer is that the horizon is not a place where forces spike, it is a place where outward directed paths stop leading outward. Crossing it changes which events can influence the rest of the universe, and that change is absolute. After the crossing, every future directed path stays inside, even if the traveller still feels weightless and still hears their own breathing. The dread comes from the word future, because the horizon is really a statement about what tomorrow can reach. Outside the horizon, you can choose trajectories that keep options open, including trajectories that send signals outward and trajectories that turn around. Inside, the set of possible futures collapses to a narrower cone, and outward becomes a direction like yesterday. You can point your rocket any way you like, but the geometry has already decided which way time points. The traveller can still look outward for a time, and the view can be strangely beautiful. They can still receive light from the universe behind them, and that light can appear blue-shifted and distorted by aberration. Blue shift here means the opposite of what the distant observer sees, because the traveller is falling into the well. Photons from behind can catch up with increasing energy in the traveller's frame, concentrating the outside sky into a bright, compressed patch. But they cannot send a message that reaches infinity once the horizon is crossed, no matter how powerful the transmitter. The boundary is not a barrier in space, it is a barrier in causality, and causality is the deeper constraint. To make this concrete, imagine sending a steady stream of pulses back to a distant friend, one pulse every second by the traveller's clock. Far away, the friend receives pulses that arrive slower and slower, and each pulse is redder and fainter. At first, the friend can still decode them, hearing a stretched out rhythm like a song played at ever lower speed. Eventually, the friend receives no usable information, even though the traveller keeps emitting pulses on their own schedule. The outside world does not see a final moment, it sees an endless fading, because the last steps are smeared across an infinite span of distant time. The horizon hides the act of crossing not by secrecy, but by the relentless thinning of communication. This is why black holes look like they swallow without showing the swallow itself. The last visible stages are not a dramatic plunge, but a long retreat into darkness created by redshift and delay. Near the horizon, light also stops behaving like straight lines in Euclidean space. even when it travels at the universal speed limit. Photon paths curve strongly, and the black hole becomes a lens that can magnify, duplicate, and sometimes imprison light. In weak gravity, lensing is a subtle distortion, a slight shear of background galaxies. In strong gravity, the bending becomes theatrical. Starlight can loop, cross itself, and arrive from directions that feel impossible. There is a critical region called the photon sphere, and it is one of the most important landmarks outside the horizon. For a non-spinning black hole, it lies outside the horizon, where photons can orbit in unstable loops. Unstable is the key word, because these are not safe, circular tracks like planets enjoy. A tiny perturbation sends the photon either outward to escape or inward to be captured, so the photon sphere acts like a razor's edge in the light map. If we could draw the paths, we would see a tangled web of curves, some grazing the black hole and whipping around like a lasso. Many of the photons that form the bright ring have circled once, or more than once, before finally escaping. This region helps explain why images of black holes show rings and shadows, even though there is no luminous surface. The bright ring comes from light that skims near these unstable paths, looping before escaping toward us. The shadow is not the horizon's silhouette like a solid object blocking a spotlight. It is the set of directions on the sky whose light rays end at the horizon, leaving a dark deficit where the background should have been. The Event Horizon telescope image fits into this logic, and its achievement is as much computational as it is instrumental. It does not photograph a surface. It constrains the geometry by mapping where light can and cannot go. That image also carries a historical echo, because the idea of a dark star predates Einstein by centuries. Yet only with general relativity, and later with radio interferometry spanning Earth, did the shadow become a measurable prediction rather than a philosophical curiosity. As we descend, the lensing becomes more severe, and the sky turns into a distorted atlas. Background stars can be duplicated, smeared into arcs, or wrapped into partial rings, because the same source can reach us along multiple curved paths. For the traveller, this means the outside universe can appear rearranged into a bright, warped halo. Light from behind can be bent forward, and the familiar constellations can fold into themselves like reflections in a curved mirror. Even the blackness has structure, because the shadow is not merely absence but a boundary of capture. It is a region where every line of sight traced backward ends at the horizon rather than at a star. Yet the traveller's biggest threat is not light, and it is not the silence of radio contact. It is the gradient of gravity across their body, which produces tidal forces that cannot be transformed away. Tidal forces stretch and compress because gravity is stronger at one end of the body than the other. Feet feel a stronger pull than the head in a feet-first fall, so the body is stretched lengthwise. At the same time, sideways directions are squeezed because the geometry focuses nearby trajectories inward. The combined effect is the classic picture called spaghettification, vivid in name because it is vivid in consequence. This is not only a dramatic image, it is a quantitative prediction that can be calculated from spacetime curvature. Tidal strength scales roughly with the mass divided by the cube of the distance, so gradients explode as you approach small radii. Curvature is the deeper word here, because it measures how neighbouring free-fall paths converge or diverge. Even when you feel weightless, the separation between your head and your feet is being driven by the geometry itself. Black hole mass changes the experience at the horizon, and the difference can be counterintuitive. For a stellar mass black hole, the horizon is small, so the gradient there can be lethal. In that case, the crossing is not a quiet step over an abstract line, because the body may be torn apart before it can learn what the horizon feels like. The point of no return can arrive with violence, not because of the horizon, but because the curvature is already intense. For a supermassive black hole, the horizon is enormous, spread across millions or billions of kilometers. At that larger radius, the gradient at the horizon can be gentle, and the crossing can be locally uneventful. This is a crucial misconception to correct, because popular images often place a glowing, shredding rim at the boundary. The horizon is not automatically a shredding zone, and it is not a luminous membrane. The violence depends on where the tidal forces become large, not on the horizon itself. A large black hole can let you cross intact, only to destroy you later as you approach the deep interior where curvature rises sharply. From the distant observer's view, these tidal details are hidden by the same redshift that hides the crossing. The outside world sees a fading object, not a body being stretched in real time because the relevant signals are being diluted into invisibility. From the traveller's view, the outside universe does not slow down in the same way, and that asymmetry matters. They can see external events appear sped up, because light from the outside is arriving from later and later times. It is tempting to imagine watching the universe race forward to its end, but the geometry does not grant unlimited spectacle. There is a limit to what they can see before the end, because their remaining proper time is finite. The outside universe does not have infinite time to send them infinite news, and many photons simply cannot catch up. The traveller's window on the cosmos narrows, even as the outside seems to accelerate within that shrinking frame. So the two perspectives are not symmetric, and the mismatch is the point. The outside can watch an endless approach that never completes, while the traveller experiences a completed crossing and a short remaining future. This difference is a lesson in coordinates, not a contradiction in physics, and it is one of relativity's most subtle gifts. The horizon is where the far observer's time coordinate becomes a poor guide to what the traveller experiences. General relativity allows both descriptions because it separates coordinate time from proper time with surgical precision. Proper time is what a clock measures along a world line, and that is what the traveller lives. The far observer's time is still useful for astronomy, because it matches how telescopes actually collect signals. It predicts that signals from near the horizon are delayed and redshifted, and that prediction matches how strong gravity sculpts spectra and timing. This is why accretion emission changes near the inner edge, where orbital speeds become a significant fraction of light speed. Photons born deeper in the well climb out redder, and many never climb out at all. It is also why jets are such valuable messengers, and why they appear as narrow, persistent beams across intergalactic distances. They are launched outside the horizon, where information can still escape, and they carry signatures of near-horizon conditions without crossing the causal line. But the horizon itself remains a hard limit for electromagnetic observation, no matter how sensitive our detectors become. Light that originates inside cannot reach us, and light that tries to hover at the boundary is infinitely redshifted in the far description. Even if matter outside the horizon heats and glows, the horizon does not shine in the classical picture. What we see is the environment, plasma, magnetic fields, shocks, and spiraling orbits arranged around a region that refuses to send light back. This is where the story introduces a quieter tension, one that is less visual but more profound. If nothing escapes, what happens to what falls in, including the information that describes it? Classically, the answer sounds simple, and it has the cold clarity of a locked door. The information is carried inward with the matter, and the outside universe loses access to it once the horizon is crossed. Quantum theory makes that simplicity uneasy, because quantum evolution is usually reversible in principle. Information is not supposed to vanish, so black holes become a test of whether our rules can coexist when gravity is strong. This puzzle did not emerge from science fiction, but from careful arguments about thermodynamics and radiation. When Hawking showed that black holes should emit a faint quantum glow, the horizon stopped being merely a one-way boundary and became a stage for deeper accounting. We do not resolve that problem here, but we name it, because the horizon is where the questions sharpen. The horizon is where gravity and quantum principles begin to argue, and the argument will shape later chapters. For now, we stay with what is solid in classical relativity, because it already overturns intuition. The horizon is locally ordinary for a large black hole, yet globally decisive because it redraws the causal map. The traveller crosses without fanfare, but their ability to affect the outside ends at that boundary. The outside never receives a final postcard, only a fading sequence that asymptotically dies away. The photon sphere and lensing explain the ring-like images in the shadowed centre, giving shape to what cannot be seen directly. Time dilation and redshift explain why the last light is stretched into weakness, and why the approach looks like an endless hesitation. Tidal forces explain why the descent can be gentle or fatal, depending on mass and on how close you are to the deep interior. The horizon is not the danger by itself, but it is the commitment. So the point of no return is not a cliff edge you see coming, and it is not marked by a sudden jolt. It is a line in space-time that separates two kinds of future, and it is crossed in silence. We end this chapter with a boundary that hides what comes next, and that concealment is built into the structure of light. We cannot see inside with light, and we cannot send probes that report back after crossing. But the universe has another messenger that does not rely on photons climbing out, and it does not care about darkness. gravity itself can carry news through changing curvature, and it can reach us from events light cannot fully explain. Next, we shift from images to ripples, trading the language of photons for the language of spacetime strain. We follow gravitational waves and the geometry they reveal as the descent continues beyond the reach of light. Light cannot report from inside a horizon, and even near it photons are delayed, reddened and drained of usable information. The closer you look, the more the signal is stretched in time, until it becomes effectively silent. Yet gravity has its own messenger, and it does not rely on glowing gas or transparent space. When massive objects accelerate, spacetime itself carries the news outward as a propagating disturbance. Gravitational waves are not light and not particles in the usual sense, even though quantum language sometimes tempts us to imagine gravitons. They are travelling distortions of geometry, a changing pattern of distances and times that sweeps across the universe. In plain terms, the ruler you trusted a moment ago is briefly rescaled, then restored. They pass through dust, plasma and darkness with almost no absorption because they couple weakly to matter and strongly to mass energy as a whole. This is the pivot in our journey toward the centre. We cannot watch horizons directly, but we can hear spacetime ring when black holes collide, and that ringing is not metaphorical. The signal is not an image, and it is not a photograph of an object. It is a time series of strain, a measured stretching and squeezing that arrives like a faint tremor after a distant catastrophe. A passing wave changes the separation between two free masses by a tiny fraction, and it does so in a very specific pattern. One direction lengthens while the perpendicular direction shortens, then the pattern reverses as the wave oscillates. The effect is quadrupular, meaning it has a four-lobed symmetry rather than a simple push-pull. That shape is not a design choice. It follows from conservation laws and the fact that gravity has no dipole radiation for isolated systems. If you could see it, the visual would be unsettlingly clean. A circle of test particles becomes an ellipse, then an ellipse rotated by 90 degrees, then a circle again. Time itself is involved, because the wave is a distortion of space-time, not merely of space. The wave carries energy and momentum, and in doing so it can back-react on the source, tightening orbits and reshaping the final plunge. The challenge is scale, and it is difficult to overstate how extreme it is. Typical astrophysical strains at Earth are around 1 part in 10 to 21, even for violent mergers. That means a 4-kilometre arm changes by less than 1,000th of a proton's diameter. In everyday language, the detector is asked to notice a change smaller than any atom spread across a distance you could drive in minutes. The idea that such waves should exist is old, but it was never easy. Einstein's equations allow wave solutions, yet for decades there was debate about whether the waves were real or merely coordinate artifacts. By the mid-20th century, work by Bondi, Sachs and others clarified the meaning of gravitational radiation at infinity, and the Hulse, Taylor binary pulsar, later supplied indirect evidence through orbital decay. That system was losing energy at exactly the rate general relativity predicted for gravitational wave emission, but the waves themselves remained unheard. LIGO was built to measure that impossibility, and its design is a study in disciplined paranoia. 2 long perpendicular vacuum tunnels act as arms of a laser interferometer, isolated from air, dust and most thermal drift. Light bounces between mirrors, and the returning beams interfere to reveal differential length changes. The interference pattern is the readout, translating geometry into brightness fluctuations that can be digitized and analyzed. In the mind's eye, the instrument is stark and geometric. Straight corridors vanish toward the horizon of the landscape, and at each end a mirror hangs as if floating, suspended by multiple stages of glass and steel. The vacuum is not a detail. It removes refractive noise and acoustic coupling that would swamp the signal. Even the ground is treated as an enemy, because Earth itself is restless. Virgo in Europe adds a third baseline and a different noise environment, which matters because noise is never identical in 2 places. Kagra in Japan adds a detector underground with cryogenic mirrors, reducing seismic disturbance and thermal agitation. Together they form a network that can confirm signals and triangulate sky position. A 4th site changes everything, because timing and polarization information multiply rather than merely add. The detectors do not record a clean tone, and they never have. They record a buried pattern inside seismic motion, thermal noise, and quantum shot noise from the discrete nature of photons. At low frequencies the ground heaves, at mid-frequencies the suspensions and coatings whisper, and at high frequencies photon counting statistics dominate. Extraction is statistical, using matched filtering against waveforms predicted by relativity, and the process resembles listening for a familiar melody in a storm. Matched filtering works because the signal is coherent, while most noise is not. You slide a predicted waveform across the data, and you ask where the correlation spikes. The templates are not arbitrary, because they are constrained by the field equations and by decades of approximation methods. Post-Newtonian expansions describe the early and spiral, effective one-body models bridge regimes, and numerical relativity anchors the violent end. The result is a library of possible songs, each with its own masses, spins, and orientations. On September 14, 2015, the pattern arrived, and it arrived in two places almost at once. It was named and it lasted a fraction of a second in band, yet it carried a story billions of years long. Two black holes, about 30 solar masses each, spiraled together and merged, releasing a final burst that briefly outshone the stars in gravitational power. The event was seen first in the Livingston detector, then milliseconds later in Hanford, with the right delay for a wave crossing a continent. This was not a subtle confirmation of an old idea, and it was not a marginal improvement in a plot. It was direct evidence that black holes collide, merge, and radiate energy through gravity, exactly as the theory demanded. In that brief moment, several solar masses of energy left as gravitational waves, converted from orbital binding energy into spacetime motion. The luminosity for an instant exceeded that of all the visible stars combined, although no light announced it. The waveform had a simple arc that carried enormous information, like a signature written in a single stroke. First came the inspiral, a rising tone often called a chirp because it climbs in frequency as the orbit tightens. Then came the merger peak, when the horizons joined into one connected region. Then came ringdown, when the remnants settled and the space-time vibrations decayed into silence. Inspiral is the long dance before contact, and it is where the signal is most predictable. Two compact objects orbit, losing orbital energy to gravitational radiation, and their separation shrinks steadily. As energy drains away, the orbit tightens and the orbital frequency increases, pulling the gravitational wave frequency upward as well. The wave frequency is roughly twice the orbital frequency, because the quadrupole pattern repeats every half orbit. Frequency rises because the bodies move faster as they draw closer, and relativity insists that faster motion means stronger time-varying curvature. Amplitude rises because the changing quadrupole moment grows stronger, and because the system's acceleration becomes more extreme. The result is a chirp that climbs in pitch and loudness until the final plunge, compressing what might have been millions of years into seconds of detectable evolution. The chirp is not just a dramatic sound, and it is not merely a convenient metaphor for audiences. Its phase evolution encodes the chirp mass, a particular combination of the two masses that controls how quickly the frequency sweeps upward. In practice, the chirp mass is measured most precisely, because it dominates the early and spiral phasing. Small differences in mass ratio and spin leave measurable imprints, appearing as subtle advances or delays in the accumulated phase. Mass sets the overall timescale, and it also sets where the loudest part of the signal lands in the detector band. Heavier systems sweep through the detector band more quickly because their characteristic frequencies are lower and merger happens earlier in frequency. Lighter systems chirp longer, giving more cycles to measure, and those extra cycles sharpen parameter estimates. The detector's sensitivity curve matters here, because it is not equally sensitive at all frequencies. Spin complicates the story in a useful way, because it couples to the orbit and changes the geometry of the inspiral. Spins aligned with the orbit can delay the inspiral and shift the phase, effectively adding support against the plunge. Misaligned spins can cause precession, modulating amplitude and polarization as the orbital plane wobbles. In the data, precession can look like a slow breathing or twisting of the waveform, and it helps break degeneracies that would otherwise hide the true configuration. These are the same spins that mattered for disks and jets, and the connection is not accidental. In electromagnetic astronomy, spin is inferred through models of hot plasma, reflection spectra, and the inner edge of accretion flows. In gravitational waves, spin is written directly into the geometry-driven phasing, with fewer astrophysical assumptions. The cost is that the signal must be loud enough because subtle phase effects are easy to lose in noise. The waveform also carries orientation information, which is crucial because the same system can look very different from different angles. The polarization pattern depends on how the orbit is tilted relative to us, and on where the detectors sit on Earth. With multiple detectors, we can separate polarizations and reduce degeneracies between distance and inclination. That matters because amplitude alone cannot tell you whether a source is nearby and edge on, or far away and face on. Then the inspiral ends, and approximation breaks, because the system is no longer gently perturbed. Near merger, velocities approach a significant fraction of light speed, and spacetime curvature becomes violently dynamical. The gravitational field is no longer a small correction to Newtonian intuition, and the bodies cannot be treated as point masses with weak interactions. Numerical relativity is needed to compute the waveform through this regime, solving Einstein's equations on supercomputers with careful control of gauge and boundary conditions. Merger is the moment when two horizons become one, and the language must be chosen carefully. It is not a collision of surfaces, because horizons are causal boundaries rather than material shells. It is a topological change in the region of no return, driven by the full nonlinear equations. In visualizations, two dark spheres distort, touch, and fuse. Yet what is really fusing is the structure of causality itself. The peak of the signal marks the most intense gravitational wave emission, and it is brief because the system is rapidly exhausting the last accessible orbital energy. The system radiates angular momentum and energy in a final surge, and the orbital motion ceases to exist as a separate entity. The remnant black hole is born hot in a geometric sense, distorted and ringing, with its horizon settling toward a smooth Kerr shape. Even the horizon area increases, consistent with the classical area theorem, as if the universe is keeping an accounting ledger. Ringdown is the settling phase, and it is where the remnant reveals its identity most starkly. The remnant emits gravitational waves at characteristic frequencies and damping times, and those parameters depend on the remnant's mass and spin. These are quasi-normal modes, like the dying vibrations of a struck bell, but with an important difference. The bell vibrates in a material, while the black hole vibrates in spacetime itself. The analogy is limited but powerful, because it gives the ear a way to understand the mathematics. A bell's tone depends on its shape and material, and imperfections split and shift the spectrum. A black hole's ringdown depends on its mass and spin, and in general relativity on nothing else. The simplicity is almost suspicious, and that suspicion is exactly what makes it testable. This is the no-hair expectation in operational form, and it is not merely a slogan. For an astrophysical black hole, electric charge is negligible, because surrounding plasma neutralizes it quickly. The Kerr solution should describe the exterior, and if Kerr is right, then the ringdown spectrum is a fingerprint with only two parameters. In that view, the messy history of the merger is erased, leaving only a final state described by conserved quantities. The dominant mode gives a clean estimate of the final mass and spin, because it carries most of the power and damps more slowly. Subdominant modes, if measured, provide consistency checks, because they should line up with the same Kerr parameters. If multiple modes match one Kerr black hole, the exterior behaves exactly as relativity predicts. If they do not, the discrepancy points to either new physics or unmodelled systematics. This is why ringdown is more than an epilogue, and why the last few cycles matter so much. It is a test of whether the remnant is a classical black hole with a horizon, because horizons absorb and do not reflect. It is also a test of whether gravity itself follows Einstein's equations in the strong field regime, where curvature is high and dynamics are fast. In that regime, small theoretical deviations can accumulate into measurable spectral shifts. The tests begin with internal consistency, because the waveform contains multiple ways to infer the same quantities. Inspiral predicts what the final mass and spin should be after energy loss, using energy and angular momentum balance. Ringdown measures those parameters again, using the quasi-normal mode spectrum. Agreement supports the picture of two black holes forming one Kerr remnant, and it strengthens confidence that the templates are not merely fitting noise. The tests also search for deviations, and they do so in several complementary ways. Modified gravity theories can change the phase evolution, the merger dynamics, or the quasi-normal mode spectrum, sometimes by introducing extra fields or modified dispersion. Exotic compact objects can mimic in spiral, but differ at the end, because their boundary conditions are not those of a horizon. The key is that the late-time behaviour is sensitive to what happens near the would-be horizon, where the effective potential and absorption properties matter. We should be clear about what is being tested, because the temptation is to overinterpret. Gravitational waves probe the exterior dynamics in the near-horizon region during merger, where the geometry is rapidly changing. They do not deliver a map of the interior, because the interior remains causally disconnected once a horizon forms. The data are a report from outside, and that limitation is part of the story rather than a flaw. Still, the horizon leaves an imprint, and it does so through boundary conditions that shape the response. In general relativity, a true horizon absorbs perturbations, allowing energy to flow inward without reflection. It provides a boundary condition that shapes the ring down and damps the modes, setting the decay times. In effect, the horizon behaves like a one-way membrane for classical disturbances. If there were no horizon, the boundary condition could change, and the waveform could carry a faint aftertaste. A surface or reflective layer could send perturbations back outward, returning energy that would otherwise be lost. That could produce late-time features not expected for Kerr, appearing after the main ring down has faded. The question becomes almost auditory. After the bell seems to stop, do we hear a delayed reply? This is where the idea of echoes enters, and it is both alluring and treacherous. If a compact object is almost a black hole but horizonless, waves could bounce between a potential barrier near the photon sphere and an inner surface. The result could be repeating, delayed pulses after ring down, spaced by the light travel time in that cavity. The delay would depend logarithmically on how close the surface sits to the would-be horizon, making the effect exquisitely sensitive to microscopic structure. Echo searches are an attempt to listen for that extra structure, and they force analysts to confront the limits of inference. Echoes would be weak, model-dependent, and easily confused with noise fluctuations or imperfect waveform modelling. The detectors are not quiet laboratories. They are kilometre-scale instruments on a vibrating planet. A claimed echo must survive careful accounting of glitches, calibration uncertainties, and the look-elsewhere effect that haunts any search across many possibilities. So far, evidence remains tentative, and the community has treated it with appropriate caution. Some analyses have claimed hints, others have not reproduced them, and statistical significance is fragile when signals are near the noise floor. The conservative statement is that current data do not require echoes, and that the simplest Kerr interpretation remains sufficient. Yet the very act of searching is valuable, because it clarifies what kinds of deviations are still allowed. Even without echoes, gravitational waves constrain alternatives, and they do so in a way that is difficult to evade. They limit how much the waveform can deviate from general relativity without being noticed, across in spiral, merger, and ring down. They bound the size of possible corrections to dispersion, polarization content, and strong field dynamics. Each new detection narrows the space in which exotic models can hide, even if no single event is decisive. One clean class of tests checks propagation, because the wave travels for hundreds of millions or billions of years before it reaches Earth. If gravitons had mass, waves of different frequencies would travel at different speeds, producing a frequency-dependent arrival time. Observations show gravitational waves arrive consistent with light speed, within tight bounds, and the constraints improve as the catalogue grows. The result is not just a number, it is a statement that spacetime's messenger is remarkably faithful over cosmological distances. Another class checks the inspiral phasing, where the mathematics is precise, and the signal contains many cycles. Parameterized deviations can be inserted into the post-Newtonian expansion, altering coefficients that control the phase at different orders of velocity. The measured coefficients agree with general relativity within uncertainties across many events, and the agreement spans different masses and spins. This matters because different systems probe different parts of parameter space, and consistency across them is harder to fake. The strongest drama sits at ring down, because it is where the final object is supposed to be simplest. If the remnant is Kerr, its mode frequencies and damping times are fixed once mass and spin are known. Measuring more than one mode is like overdetermining a suspect's identity, because the spectrum must self-consistently point to the same parameters. A mismatch would not merely be an error bar, it would be a crack in the idea that horizons erase complexity. This is called black hole spectroscopy, and the name is deliberately ambitious. It is not yet routine, because signal to noise is limited and subdominant modes are faint, but each observing run increases the catalogue and improves the odds of a loud event, perhaps one close enough or massive enough to ring clearly. The future promise is a set of spectra, not just single tones, turning black holes into test masses for strong field gravity. The catalogue also changes our astrophysical picture, and it does so with every new detection. We now know there is a population of stellar mass black holes heavier than many X-ray binaries suggested, implying different evolutionary histories. We see mergers at cosmological distances, meaning the universe has been producing these events for much of its history. The rates and masses imply formation channels that are still debated, and the debate is constrained by data rather than preference. Some binaries likely form from isolated, massive stars that evolve together, shedding envelopes and surviving supernova kicks. Others may form dynamically in dense clusters, where black holes sink to the center through mass segregation and pair up through close encounters. Spin distributions and eccentricity constraints help separate these pathways, because dynamical formation can leave misaligned spins and residual eccentricity. Even the absence of eccentricity is information, because it tells us the system had time to circularize before entering the detector band. These formation stories matter for our central question, because they describe how often horizons are created in violent mergers. They tell us what kinds of black holes exist, how fast they spin, and how frequently the universe builds new Kerr remnants. The universe is manufacturing horizons continuously, and it is doing so in environments we can barely imagine. Each merger is a natural experiment, repeating the same strong field process under slightly different initial conditions. The detectors also reveal what they cannot yet do, and those limitations shape the narrative. Localization is often coarse, limiting electromagnetic follow-up for black hole mergers, because timing alone gives wide sky arcs. For neutron star mergers, light can appear, and the combined story becomes richer. For black holes, the signal is gravity alone, and the darkness is part of the evidence. That silence is itself a clue, and it has a clean physical explanation. A black hole merger in vacuum should not produce light, because there is no matter to heat and no magnetic turbulence to radiate. If gas is absent, there is nothing to glow, and the gravitational wave becomes the primary record of the event. The universe can be unimaginably violent and still visually invisible. In this sense, gravitational wave astronomy is the purest horizon science we have, and it is pure in a demanding way. It does not depend on plasma models, radiative transfer, or magnetic turbulence, all of which can obscure interpretation. It depends on geometry and on the calibration of instruments, including laser frequency stability and mirror displacement sensing. The reward is that the signal is closer to first principles than most astronomical data. Yet the interpretation still has limits, and honesty about those limits is part of scientific strength. Waveforms are computed within general relativity, then compared to data, and that comparison assumes the theory is close to correct. If nature deviates strongly, our templates might miss it, so searches must also include unmodeled burst methods that look for coherent excess power. Those methods are less specific, but they are robust against surprises. The network approach reduces risk and increases credibility, because real waves must behave like waves. Signals must appear consistently in separated detectors with the right time delays and compatible amplitudes. Environmental disturbances are checked and vetoed, from lightning to local vibrations to instrumental glitches. Confidence comes from redundancy and from the coherence of the pattern, and from the fact that noise rarely conspires across continents. When the pattern is real, it is a direct measurement of spacetime dynamics, and that is the conceptual shift this chapter demands. It is not a picture of matter moving through space like a planet crossing a star's face. It is space itself changing, and our instruments acting as rulers that briefly lose their rigidity. The detector is not watching an object, it is being touched by the geometry of a distant event. This returns us to the horizon problem from Chapter 5, and it sharpens it. The horizon hides the crossing from light by redshift and causal structure, turning infall into a fading, slowing signal. Gravitational waves do not escape from inside either, but they are generated outside and during the last visible moments of orbital motion. They let us test the boundary conditions of the exterior, even when the interior remains sealed. They let us ask whether the remnant behaves like a Kerr black hole, defined by mass and spin alone, and whether the ring-down matches that austere expectation. They let us probe whether horizons are as clean as the equations claim, or whether something reflects, delays, or modifies the final settling. The data are not a confession from the centre, but they are a cross-examination of the edge, and the edge, in relativity, is where the deepest claims are made. So the tension shifts, and it becomes more philosophical without leaving physics behind. We are not only asking what happens to an infalling traveller, and whether their clocks and signals behave strangely. We are asking whether the object they fall into is exactly the one general relativity describes, down to its response to perturbations. If the exterior is simple, then the mystery is pushed inward, toward what cannot be directly reported. If the answer is yes, then the exterior is brutally simple, and that simplicity is itself eerie. Mass and spin determine the geometry, and the ring-down is the closing signature, like a final chord. The interior remains hidden, but the boundary behaves as expected, absorbing and erasing. The universe, in that case, offers no warning label, only a clean mathematical surface. If the answer is no, then something new is waiting near the would-be horizon, and it may be subtle enough to hide in the last cycles. It could be quantum structure, new fields, or a breakdown of classical causality, appearing as altered damping or delayed features. Gravitational waves become our best chance to detect that deviation, because they are generated by the geometry that would be modified. The question is whether the ringing contains an extra note, faint but persistent. For now, the data lean toward Einstein, and they do so across many independent checks. The observed inspirals and ring-downs are consistent with black holes predicted by general relativity, within the sensitivity we currently possess. The no-hair picture is not proven in full detail, because spectroscopy is still emerging, but it has survived every loud test so far. Each confirmation is not a victory lap, it is another tightening of the constraints. That survival does not end the mystery, and it may even deepen it. It sharpens the question, because if horizons are real and Kerr is right outside, then the centre becomes even more haunting. The exterior gives us no warning, no complexity, no hint of what the theory cannot yet explain. We are left with a smooth boundary and an unresolved interior. We have listened to collisions and heard space-time ring, and we have learned to translate that ringing into masses, spins and distances. We have used it to test the rules that govern horizons, and to search for deviations without finding a necessity for them. Now the story turns inward again, because the exterior has been interrogated as far as it can be. With horizons tested from the outside, we return to the most unsettling question. What does our best physics say happens as you continue past the boundary, heading toward the centre where curvature and meaning diverge? We have tested horizons from the outside with light, plasma and gravitational waves. Now we step into the region that cannot answer back. Inside an event horizon, the question is not what you see, because vision is just light, and light is already trapped. The question is what futures remain possible, once causality has been bent into a funnel and the outward paths have been erased. General relativity does not describe a black hole as a thing sitting in space like a rock. It describes a space-time geometry shaped by mass and energy, and the horizon is where that geometry changes the meaning of direction. Outside, you can choose to move inward or outward, and both are spatial options you can debate. Inside, the equations say the outward option is gone, like trying to travel to yesterday, not because you are weak, but because the map forbids it. This is the core idea we must hold without metaphor taking over, because metaphors can mislead when the geometry is exact. Inside the horizon, the coordinate we called radius behaves like time, and time behaves like a direction you cannot turn away from. In the simplest case, the Schwarzschild black hole has no spin and no charge, and that simplicity is a gift. Carl Schwarzschild wrote down this solution in 1916, astonishingly early in the life of relativity, and its symmetry makes the lesson sharp. At the horizon, nothing locally explodes for a freely falling observer in a large black hole, because the equivalence principle still applies in a small enough neighbourhood. The crossing can be quiet, almost anticlimactic, yet the global map of cause and effect has already closed. Imagine the visuals we use to keep ourselves honest. A grid of space-time lines, then cones of possible light paths, then the cones tipping. Light cones tip inward as you fall, and inside they tip so far that every future pointing path moves towards smaller radius. The centre is not a destination you aim for with willpower or navigation, because aiming presumes you can choose among futures. It is the only remaining tomorrow, the only direction that still counts as forward. This is not a statement about engines failing or matter freezing in place, which are popular myths. It is a statement about the structure of space-time, written into the metric and the sign of its components. The swap is often described as time and space exchanging roles, and that phrase is useful but incomplete. The deeper point is that the radial coordinate becomes time-like, so decreasing radius is as compulsory as aging and just as irreversible. If you try to hover, you do not merely need more thrust in the usual engineering sense. You would need a world line that points outside the allowed future cone, an attempt to step into a direction the geometry has declared non-physical. So the horizon is not a wall you crash into, and the interior is not a cavern you can explore with a flashlight. It is a region where the set of possible futures has been narrowed by geometry itself, until outward becomes an invalid verb. Schwarzschild's interior also gives a stark clock, and the clock is not measured by distant observers. For an infalling observer, the proper time from the horizon to the singularity is finite, and it can be surprisingly short. Proper time is the time a clock would record along your path, the time that matters to your body and your instruments. It is not the coordinate time used by someone far away, who never sees you cross in their own bookkeeping. Finite does not mean we know what happens at the end, and it does not mean the end is simple. It means classical general relativity predicts an unavoidable endpoint in a bounded amount of lived time once the horizon has been crossed. The exact duration depends on mass and on how you fall, and the scaling is part of the story. For a non-spinning black hole, the horizon size grows linearly with mass, and the characteristic infall time grows with it as well. That scaling hides a strange contrast. Bigger black holes can feel gentler at the horizon, yet they still deliver you to the deep interior. Once inside, you cannot postpone the encounter indefinitely, because postponement would require an outward future. This is where the word inevitability belongs, and it belongs in a precise sense rather than a poetic one. In classical GR, the singularity is not merely likely, it is in the causal future of interior world lines. The singularity is also where the math becomes an alarm rather than a guide. Curvature scalars diverge, geodesics end, and the theory stops giving sensible physical answers, as if the equations themselves are raising a hand. We should be careful about what that means, because infinity in an equation is not automatically infinity in nature. A divergence can signal a real physical blow-up, or it can signal that the theory is being pushed past its domain of validity. Still, before the breakdown, the interior is not gentle, and the danger has a clear mechanism. Tidal forces grow as radius shrinks because curvature grows, and curvature controls relative acceleration between nearby falling parts. Tidal forces are what the ocean does to the Earth, stretched to a cosmic extreme, and they do not care about your rocket fuel. They pull harder on your feet than your head, and they squeeze sideways as they stretch lengthwise. This revisits the earlier misconception about the horizon being the shredding zone, a dramatic image that is sometimes true but often misplaced. For a supermassive black hole, the horizon can be crossed without immediate destruction, because the curvature there can be modest. The reason is geometric scaling, not mercy and not a special property of darkness. The horizon radius grows with mass, so the curvature at that radius can be small, even while the black hole is more massive. But the interior does not stay mild, because the geometry tightens as you move inward. As you approach smaller radii, curvature rises steeply, and the same body that crossed intact becomes vulnerable to lethal stretching and squeezing. So the horizon can be survivable, yet the interior remains terminal in the classical picture, and the difference is timing. The danger is delayed, not removed, and the clock to the end is still finite. This is the Schwarzschild story in one line, and it is almost brutally clean. Inside the horizon, inward is future, and the singularity is the future boundary of the space-time. Now we complicate the story, because real astrophysical black holes are not static monuments. They spin because the stars and gas clouds that form them carry angular momentum, and spin changes the geometry outside and inside. Kerr black holes are the rotating solutions of Einstein's equations, found by Roy Kerr in 1963, long after Schwarzschild's wartime calculation. They are still vacuum solutions, yet their interior structure is far less simple than Schwarzschild's, and the diagrams become labyrinths. We already met Kerr outside through frame dragging, the ergosphere, and the possibility of extracting energy without crossing the horizon. Now we follow Kerr into the region where extraction ends, and where rotation stops being a trick and becomes a constraint. Rotation breaks the perfect spherical symmetry, and it introduces new surfaces that are not mere coordinate artifacts. The event horizon remains the one-way boundary, but it is no longer the only horizon-like structure in the math. In the ideal Kerr solution, there is an outer horizon and an inner horizon, nested like shells in a strange causal onion. The inner one is often called the Cauchy horizon, and the name is a warning about prediction itself. A Cauchy horizon marks a limit of predictability in classical GR, a place where the usual initial value problem breaks down. Beyond it, the equations no longer determine a unique future from reasonable initial data, even if you knew the exterior perfectly. That sounds abstract, yet it has a concrete meaning for our central question about what happens next. If predictability fails, then the interior is not just hidden from us, it is not even well posed in the classical sense. In textbook Kerr, the inner horizon appears as a gateway to strange possibilities, and the temptation is real. Some extensions suggest paths that avoid the central singularity, at least in the idealized geometry, as though the funnel might split. The math hints at a ring-shaped singularity and regions where the coordinate roles twist again, reshuffling what counts as time. In those diagrams there are routes that look like passages rather than dead ends, and the camera almost wants to follow them. This is where suspense belongs, because the equations tempt us with escape hatches, and the human mind loves a loophole. Yet the same equations also hint that the hatch is made of unstable assumptions, and instability is the enemy of fantasy. The ideal Kerr interior assumes perfect vacuum and perfect stationarity, as if the black hole were eternal and undisturbed. Real black holes form from collapse, accrete matter, and are constantly perturbed by infalling radiation, even if the disturbance is faint. Even a tiny trickle matters, because the inner horizon acts like an amplifier rather than a cushion. Infalling and outgoing streams are infinitely blue-shifted relative to each other near that surface, which means their energies are boosted in a runaway way. Blue shift here is not a colour change you could admire, but a compression of wave crests into tighter and tighter intervals. The closer you get to the Cauchy horizon, the more violently those waves are focused, and the more severe their measured energy becomes. This leads to mass inflation, a phenomenon discovered by studying small perturbations of the Kerr interior, and it is one of the most sobering results in black hole theory. The effective internal mass parameter grows without bound near the Cauchy horizon, even when the exterior looks calm. The phrase sounds like bookkeeping, yet it describes a physical instability that would be felt as crushing stress energy. Energy densities measured by infalling observers can blow up, driven by the extreme focusing of radiation and the feedback of gravity itself. In visual terms, the neat inner horizon of the analytic diagram begins to shimmer, then wrinkle, then tear. The inner horizon becomes a place where the clean solution likely collapses, and where smooth continuation is replaced by something singular. Instead of a doorway, the geometry may develop a violent barrier, a kind of internal storm front where curvature spikes. In that sense, Kerr does not necessarily offer a safer interior, and it may offer a more complicated route to breakdown. The breakdown is triggered by realistic imperfections, which is a crucial point about physics versus mathematics. The exact Kerr solution is a mathematical ideal, and nature rarely grants ideals in regions that amplify every deviation. Astrophysical black holes are surrounded by plasma, magnetic fields, and fluctuating accretion flows that flicker across the horizon. They are also embedded in a universe filled with background radiation and gravitational perturbations, including the faint hiss of the cosmic microwave background. Those perturbations cannot be shut off, and inside the horizon they cannot be radiated away to infinity as a release valve. The interior must carry them, and the inner horizon may punish them by turning small disturbances into dominant curvature. So when we ask what happens inside, we must separate two claims that are easy to blend together. One is what the exact solutions allow on paper, and the other is what stable, realistic collapse likely produces. Classical GR gives us strong reasons to doubt that the maximal analytic extension is physically realized in nature. The inner horizon appears to be generically unstable, and instability changes the interior's causal structure, replacing elegant diagrams with a harsher, more generic fate. We should also connect this to what gravitational waves told us in the last chapter, because that evidence is powerful but limited. Ringdown supports Kerr outside, yet it cannot certify the interior extension, because the interior is causally disconnected from the detectors. The exterior can be clean while the interior is messy, and that contrast is part of the mystery. The horizon can hide not only events, but also the failure modes of the equations that describe those events. This returns us to the central question with sharper edges, and it forces intellectual humility. What do we actually know through observation theory and hard limits about the path toward the centre? Observation gives us the exterior and the near horizon region, where matter glows before it falls silent. Theory gives us interior solutions, but theory also gives us reasons to mistrust their most exotic features, especially when small perturbations grow without bound. Inside, no signal can climb out to correct our models, and that is not a technological limitation. The interior is inferred by consistency with the exterior, by mathematical extension, and by stability arguments that ask what survives when perfection is removed. That is a strange standard compared to most of science, and the strangeness is worth naming. We are used to experiments that can report back, yet the horizon forbids the most direct kind of test, leaving us with a disciplined, indirect form of knowing. So we lean on what is constrained and what is generic, because generic behavior is what survives in the real universe. We trust the equivalence principle locally, we trust the causal structure of horizons, and we trust instabilities when they appear under small perturbations. Tidal forces give another anchor, because they are tied to curvature, and curvature is coordinate independent rather than a trick of labels. If curvature grows large, then any physical object is threatened, regardless of coordinates, diagrams, or storytelling. For a supermassive black hole, the traveller may cross the horizon intact, and may even have time to think and to watch their instruments. Yet the interior still funnels them toward regions of higher curvature, where the gradients become too steep for matter to remain coherent. For a stellar mass black hole, the traveller may be torn apart before or near the horizon, because the curvature scale is tighter. The difference is not the existence of the horizon, it is the scale of curvature at crossing and the brutal efficiency of tidal acceleration. Either way, the interior is not a place where you can set up camp or send a report. It is a region where the geometry forces convergence, and where the physical environment becomes less like space and more like a countdown. In Schwarzschild, that convergence is monotonic and simple, and that simplicity is chilling. In Kerr, the convergence is tangled with rotation, and the math introduces inner horizons and potential detours, as if the funnel had eddies. But the detours are likely illusions of perfection rather than routes a real object could follow. Mass inflation suggests that the inner horizon becomes a singular feature, turning the would-be pathway into a destructive boundary, and turning predictability into a casualty. This is a moment to be explicit about what we mean by singularity, because the word is often treated like a location. It is not a point you can picture, it is a breakdown of the space-time description, where geodesics cannot be extended. A geodesic is the closest thing relativity has to an inertial path, the route of free fall when no forces intervene. When geodesics end after finite proper time, the theory is telling us that space-time, as described, is incomplete. The singularity is therefore both a destination in the equations and a warning sign about the equations, and both meanings matter. It tells us that classical GR is incomplete, not merely dramatic, and that the interior is where that incompleteness becomes unavoidable. We cannot finish the journey with Einstein alone, because Einstein's equations predict their own failure at the end of the classical road. The centre is where the theory stops being a guide, and where any confident narration must become conditional. Quantum physics is the obvious missing ingredient, because matter and radiation are quantum, and because extreme curvature suggests quantum gravitational effects should matter. Yet we do not have a complete quantum gravity theory to deploy, only partial frameworks and competing hints. This is why the interior remains mysterious even when the exterior is well tested, and the contrast is not a contradiction. The horizon seals the region from observation, and the singularity signals the breakdown of our classical description, leaving a gap that theory cannot yet close. Still, the interior teaches a disciplined lesson, and it is more than a horror story. The event horizon is not just a line you cross, it is a reordering of what can count as a future, and that reorder is a physical statement about light cones. Inside, time becomes directional in a new way, and the language strains to keep up. The coordinate that measured distance to the centre becomes the parameter that must decrease. Like a countdown you cannot pause, and like a clock with only one hand, that is the eerie simplicity of the Schwarzschild interior, and it is why it remains the canonical lesson. The centre is not a place you might reach, it is the only remaining endpoint of time-like motion, and the geometry insists on it. That is also the uneasy complexity of the Kerr interior, and it is why it remains a frontier of debate. The equations suggest additional structure, yet the same equations suggest that structure is unstable under realistic conditions, and that instability may erase the neat pathways. So our knowledge is layered, and the layers have different kinds of certainty. We know the horizon's causal meaning, because it is defined by light cones and tested by exterior dynamics, and because it is the boundary of what can send signals outward. We know that for large black holes, crossing need not be locally violent, because curvature at the horizon can be small for big masses. We know that deeper in, curvature rises and tides become lethal, because that follows from invariance rather than coordinates. We know that classical GR predicts finite proper time to a singularity in the simplest case, and that this prediction is not a matter of perspective. We know that rotation complicates the interior, and that inner horizons likely suffer mass inflation, making the ideal extension physically suspect. What we do not know is what replaces the singularity, or what the true interior geometry is when quantum effects and realistic perturbations are included. The horizon keeps that answer from being directly measured, and the math keeps warning us where it stops being trustworthy. This is the documentary's tension made explicit, and it sharpens as we move inward. The closer we get to the centre, the more the story becomes about limits, not only of travel, but of inference. We can describe what must happen to causal structure once a horizon forms, because that is built into the definition of an event horizon. We can describe what classical solutions predict if we extend them inward, and we can test those solutions indirectly through their exterior fingerprints. But we cannot verify the interior by communication, and we cannot trust the equations where they diverge, even if the divergence is mathematically consistent. The centre is both a predicted endpoint and a signpost that prediction has run out, and that duality is the honest conclusion. So we end this chapter with a careful turn. The word singularity is not a satisfying answer, it is a placeholder for missing physics. Next, we confront what that missing physics might demand, without pretending the demand is already met. We follow the questions that horizons force on quantum theory, information, and the meaning of a boundary that hides everything forever. We have followed the evidence as far as the universe lets it speak. Outside the horizon, light and gravity still carry messages we can test. Telescopes track stars, interferometers catch ripples, and timing arrays listen for slow cosmic beats, each method stitching constraints onto the same exterior picture. Inside, the story changes from measurement to extrapolation, because the horizon blocks any direct return signal. The equations keep going, but their answers become warnings, like a map whose ink grows darker as the terrain turns unknown. The word singularity sounds like a place, like a point you could draw on a chalkboard. In relativity, it is a diagnosis, not a picture, and the diagnosis is about the failure of the model's own rules. A singularity means the classical spacetime description fails in a precise way. It is where the theory stops being able to extend its own predictions, even though the equations themselves still look perfectly well formed. One definition is geodesic incompleteness, a phrase that sounds technical because it is. A freely falling path ends after finite proper time, even though nothing locally commands it to stop, and that abrupt ending is the mathematical alarm bell. A geodesic is the closest thing to inertial motion in general relativity. The path an accelerometer would call weightless. If geodesics cannot be continued, spacetime is incomplete as a physical model, because the theory cannot say what an unforced observer experiences next. Another signal is diverging curvature, which is not about coordinates or bad choices of labels. Quantities built from the Riemann tensor can blow up, implying unbounded tidal distortions in the classical geometry, the kind that would stretch and squeeze any extended object without limit. These are not coordinate tricks like the horizon once was, where a clever change of variables restores calm. Curvature scalars and incomplete geodesics are invariant statements, independent of how we label events, and that invariance is why the singularity carries such weight. So the singularity is not merely a dramatic endpoint for an infalling traveller. It is general relativity predicting the boundary of its own applicability, a boundary defined not by ignorance, but by the theory's internal bookkeeping. This is the central mystery of the documentary. We can describe the approach, yet the destination is written in a language that breaks. Visually, it is like watching a simulation sharpen into detail, then dissolve into static at the very centre. The singularity appears because gravity in GR is geometry, and geometry responds to energy density and pressure. Under collapse, density rises and curvature concentrates, and the same mechanism that makes orbits and lenses also drives the interior toward extremes. Einstein's equations tie curvature to the stress-energy tensor, and they do so locally, point by point. That local link is powerful, yet it also means that if matter is compressed enough, the geometric response can become violent. The Penrose and Hawking singularity theorems formalize the trap with careful logic. Under reasonable conditions, horizons and energy constraints imply incomplete geodesics, so the breakdown is not a special feature of one exact solution. Those reasonable conditions are not arbitrary, even if they sound abstract in narration. They include assumptions like positive energy density along light rays and the existence of trapped surfaces where even outward-directed light converges inward because spacetime itself is tilting. The theorems do not say what the singularity is made of, and they do not draw its shape. They say that classical spacetime cannot be complete once collapse passes certain thresholds, and that conclusion survives many changes in the details. That is a subtle but crucial shift, and it is easy to miss on first hearing. The math proves a limit, not a substance, and it proves that limit with the same rigour used to prove the horizon's inevitability. In Schwarzschild, the classical story is brutally direct and almost cinematic in its simplicity. Inside the horizon, decreasing radius is as unavoidable as moving into the future, because the roles of space and time effectively trade character. An infalling observer does not choose to head toward the centre in the usual sense. The geometry makes R behave like a time coordinate, and the singularity becomes a kind of tomorrow, approached not by steering, but by the passage of proper time. In Kerr, rotation complicates the interior with inner horizons, frame dragging, and regions where the naive extension suggests strange causal structures. Yet mass inflation suggests the idealized extension is physically fragile, because tiny perturbations can amplify into enormous energy densities. The inner horizon, in that picture, acts like a focusing surface for radiation and infalling debris. What looks smooth in an exact metric can become unstable when the black hole is treated as an astrophysical object, fed by a messy universe. Either way, the common feature is a region where curvature grows beyond any scale we have tested. It is where the smooth manifold picture becomes suspect, and where the word space-time may be more assumption than fact. At this point, physics has to ask what it usually avoids, because success has carried us to the edge. What happens when a successful theory produces infinities and incomplete paths, and does so not by accident but by necessity? In other fields, infinities often mean a missing layer of description, not literal infinite quantity in nature. They can mark where a new theory replaces an old approximation, the way fluid equations fail when molecules matter. The classic example is the ultraviolet catastrophe in thermal radiation, where classical physics predicted infinite energy at short wavelengths. Quantum theory did not patch the infinity, it replaced the assumptions that created it, and the catastrophe became a clue. The singularity problem invites the same suspicion, and it does so with the same emotional rhythm. General relativity may be an effective theory that fails when gravity becomes quantum, accurate in its domain yet incomplete at the deepest scales. That brings us to the Planck scale, the regime where dimensional analysis starts to shout rather than whisper. Combine G, C and H and you get a length around 10 rho 35 meters, a scale so small it defeats ordinary visualization. At that scale, quantum fluctuations of geometry should be unavoidable, because the act of localizing energy also gravitates. Spacetime may not behave like a smooth continuum, even in principle, and the fabric metaphor begins to fray under its own weight. The Planck time is around 10 to 43 seconds, a scale so short that our operational notions of before and after become questionable. To measure such intervals, you would need energies that would themselves curve spacetime dramatically, turning the measurement into part of the phenomenon. The Planck energy is around 1019 GeV, far beyond any accelerator we can build, even in the most optimistic engineering dreams. No laboratory can directly recreate the densities that drive the classical singularity, so we cannot simply test our way inward. so we are trapped between two truths that do not comfortably coexist. The equations demand a breakdown, and experiments cannot yet guide the replacement, leaving theory to navigate with consistency, symmetry, and indirect clues. This is why the centre of a black hole is not just hidden by the horizon, it is also hidden by the gap between general relativity and quantum theory, a gap that opens widest exactly where the curvature becomes strongest. We should be careful about what we claim to know, because the temptation to overstate is strong. We know the exterior geometry is well tested, and we know horizons behave like causal boundaries, at least to the precision of current observations. We also know that quantum theory governs matter and fields everywhere we have checked, from atoms to superconductors to the early universe plasma. It's hard to believe gravity alone stays classical at arbitrary curvature, as if it were exempt from the quantum rules it helps enforce. But we do not know the correct quantum theory of gravity, and that is the honest line we cannot cross. We have frameworks, partial results, and consistency checks, not a final map, and each framework highlights different features of the unknown terrain. One possibility is that the singularity is real in some sense, and nature allows a true boundary to spacetime. Another possibility is that quantum gravity resolves it into something finite, replacing the classical endpoint with a new kind of structure. Even the word resolve can mislead, because it suggests a neat fix with familiar ingredients. The replacement might not be a gentler core, but a different concept of spacetime, where the classical question stops applying and the old vocabulary becomes inadequate. If we keep the narrative honest, we must say this clearly and without theatrical escape hatches. The singularity is where physics admits it does not know, and that admission is itself a result earned by decades of theory. Now the stakes widen beyond one falling observer and beyond one dramatic diagram. If singularities exist, they threaten predictability, because classical evolution ends at a boundary where the equations no longer define a unique continuation. In GR, predictability is tied to global hyperbolicity and well-posed initial value problems, the idea that data on a suitable slice determines the future. A singularity can act like a tear in the causal fabric, where the notion of future determined by past becomes mathematically fragile. That is why cosmic censorship enters the story, not as a decorative conjecture but as a protective principle. It is a conjecture about whether nature hides these tears behind horizons, keeping the breakdown from contaminating the rest of spacetime. The weak cosmic censorship hypothesis says singularities formed by collapse are not visible from infinity. The horizon covers the breakdown, preserving external predictability, so distant observers never receive signals from the region where the classical laws fail. The strong version goes further, and its ambition is easy to underestimate in a single sentence. It suggests that for generic conditions, spacetime remains globally predictable, with no naked Cauchy horizons accessible to observers, so determinism survives in the broadest possible sense. Cosmic censorship is not proven in full generality, and that lack of proof is itself telling. It is a guiding principle shaped by what would otherwise go wrong in the theory, and by the uneasy feeling that naked breakdowns would make physics feel optional. If a naked singularity existed, signals could emerge from a region where classical laws fail, and those signals could influence the outside world. The universe would present outcomes not determined by prior data, not because we are ignorant, but because the model would be incomplete. That would not just be strange in a philosophical way, it would be operationally devastating. It would undermine the idea that physics can predict, even in principle, what comes next. Because the next could depend on unknowable boundary conditions at the tear. There are hints and counterexamples in idealized settings, and the literature is full of careful caveats. Some finely tuned solutions produce naked singularities, but the question is whether they survive realistic perturbations, the messy imperfections that real stars cannot avoid. Rotation complicates this, because Kerr has an extremal limit, a sharp bound relating mass and spin. If spin exceeded a certain bound, the horizon would disappear in the classical solution, leaving the interior exposed in a way that feels like a violation of the story's rules. Astrophysical processes seem to prevent that overspinning through radiation, accretion dynamics, and instability. Yet the censorship question remains a live frontier, because seems to is not the same as a theorem, and nature has surprised us before. So the horizon is doing double duty in our narrative, and the visual should linger on that dual role. It hides the interior from observation, and it may also hide the failure of the classical theory. like a curtain that conceals both a stage and a missing floor. This returns to the documentary's central question, now sharpened by everything we have admitted. What do we actually know through observation, theory, and hard limits about the approach to the centre, and where does knowledge become disciplined speculation? We know what GR predicts when extended inward, and we know how that extension is carried out mathematically. We know why that prediction is mathematically sharp and why it is physically suspect, because the same extension ignores quantum effects that should grow unavoidable. Now we introduce candidate resolutions, without pretending they are settled or mutually compatible. Each is an attempt to replace the classical endpoint with quantum-consistent structure, while still reproducing the exterior success that makes black holes such compelling objects. One family comes from loop quantum gravity, where geometry is quantized rather than assumed continuous. The idea is that areas and volumes have discrete spectra, so the infinitely divisible picture of space is replaced by a granular one at the smallest scales. In some models, collapse does not reach infinite density, because the quantum geometry modifies the effective dynamics. Quantum effects produce an effective repulsion at Planck curvature, turning the classical crunch into a bounce, not unlike how quantum pressure stabilizes matter against classical collapse in other contexts. The bounce is not a promise of escape, and it is not a science fiction tunnel by default. It is a claim that the singularity is replaced by a transition, possibly to another region of spacetime, or to a phase where classical time is not the right parameter. These scenarios are still debated, and they depend on symmetry assumptions, truncations, and effective equations that may miss crucial degrees of freedom. Yet they illustrate a key point that infinities may be artifacts, produced when we push a smooth model beyond its domain. Another family comes from string theory, where the fundamental objects are extended rather than point-like, and where gravity emerges with additional degrees of freedom. That extension changes how short-distance physics behaves, because interactions are smeared over a finite length scale rather than concentrated to point. One proposal is the fuzzball picture, which reframes the interior in a radical way. Instead of a smooth horizon and an empty interior, the microstates are horizon-sized quantum configurations, complex and numerous, like a dense thicket where classical emptiness once stood. In that view, the classical black hole is a coarse-grained description, like temperature emerging from molecular motion. The centre is not a point, and the interior may not exist as classical space, because the degrees of freedom that carry entropy are spread throughout the would-be horizon region. Fuzzballs aim to address both singularities and information loss, and that pairing is not accidental. They suggest that what falls in interacts with structure, rather than disappearing into a featureless void, and that the radiation can carry detailed correlations because the object is not truly empty. There are also effective core and regular black hole models, which modify the stress energy or the gravitational action to produce finite curvature everywhere. They are often presented as phenomenological bridges, capturing what a deeper theory might do without claiming to be that deeper theory. Some replace the centre with a de Sitter-like core, where pressure counters collapse and the geometry resembles an expanding vacuum region. Others introduce non-local corrections that smear energy density, so the classical pile-up that drives divergence is softened into a finite peak. These models can be mathematically consistent within their assumptions, but they often rely on exotic matter or effective terms whose microscopic origin is unclear. Still, they serve as placeholders for a broader idea that the classical singularity might be replaced by a high curvature region that remains finite. At this stage, we should connect back to what we can test because the documentary's credibility depends on that discipline. Gravitational waves confirm the exterior behaves like Kerr, within current sensitivity, and ring-down frequencies match the expectations of a rotating horizon remarkably well. That does not tell us the interior is classical, and it does not certify the singularity as a real physical object. It tells us that any new physics must hide extremely well, or mimic GR outside the horizon, because the exterior is constrained by data that keeps improving. This is where the narrative tension tightens, and the visuals can emphasize the squeeze. The better the exterior matches Einstein, the more the mystery is forced inward, into a region that is both causally sealed and theoretically unstable. Yet quantum theory refuses to stay outside the story, because horizons are not merely geometric surfaces. Hawking radiation, even as a semi-classical calculation, ties the horizon to quantum fields, and it does so with a result that is simple to state and hard to absorb. Hawking's result says black holes are not perfectly black, because quantum fields near the horizon produce radiation with a thermal spectrum. In the usual picture, pairs of excitations are created near the horizon, and the bookkeeping of energy allows one partner to escape, while the other effectively reduces the black hole's mass. If evaporation is real, the black hole has a lifetime and an end state, even if that end is unimaginably far in the future for stellar masses. Then the singularity is not just an interior endpoint, it is part of a global history, connected to what an external observer eventually sees. This leads directly to the information paradox, which we have been circling since Chapter 5, and which now gains sharper teeth. Quantum mechanics expects unitary evolution, where information is not destroyed, and where pure states do not become mixed, without an environment that keeps the correlations. A purely thermal Hawking flux seems to carry no detailed record of what fell in, only a temperature set by mass, spin, and charge. If the black hole evaporates completely, the information appears lost, and the loss looks permanent rather than merely hidden. General relativity, with a one-way horizon, and a singularity, makes that loss feel natural, like a shredder at the end of time. Quantum theory makes it feel impossible, because the mathematics of quantum evolution does not contain a delete operation. So the singularity problem is not isolated, it is entangled with the meaning of the horizon and with whether the universe allows irreversible erasure. The centre and the surface become two faces of the same question, connected by the demand that physics remain consistent. If information cannot be lost, then something in the classical story must give, and that is the uncomfortable fork in the road. Either the horizon is not a perfect one-way boundary, or the interior is not a terminal sink, or the way we connect quantum fields to curved space-time needs revision. Some proposals keep the horizon but change the interior, letting quantum gravity replace the singularity with a region that stores correlations. Information might be stored in subtle correlations and released in the radiation over long times, so the Hawking flux is not exactly thermal when examined with perfect precision. Other proposals change the horizon itself, and that change can be gentle or violent depending on the mechanism. There could be quantum structure at or near the horizon, altering what an infalling observer experiences and forcing us to rethink the equivalence principle's promise of calm passage. The firewall debate is one sharp expression of this tension, and it is sharp because it pits cherished principles against one another. It asks whether preserving unitarity forces violent physics at the horizon, conflicting with equivalence, or whether our assumptions about entanglement and locality break first. We do not resolve that debate here, because resolution would require a completed quantum gravity theory we do not yet possess. But we must preview its logic because it shows why the singularity and the horizon cannot both remain classical if quantum theory is right. This is also where cosmic censorship gains a new dimension, beyond its classical role as a shield for predictability. If quantum gravity resolves singularities, censorship might be automatic, or it might be replaced by a different principle, one that governs how quantum information is allowed to flow. Conversely, if naked singularities were possible, they could become windows into quantum gravity, offering direct exposure to the breakdown. They would also be threats to predictability, and to the idea of stable laws, because they would let unknown boundary physics leak into the observable universe. So the center becomes a crossroads of foundational questions, and the narration should let that weight settle. What is spacetime made of, and what does it mean for evolution to be deterministic, when the stage itself may be quantized and the script may be probabilistic? We should also address a common misconception directly, because popular imagery is powerful and often misleading. The singularity is not proven to be a literal point of infinite density in nature, like a tiny bead of matter at the center. It is proven that classical spacetime, under broad conditions, cannot be extended along certain paths, and that proof is rigorous. That is a statement about the model, not a photograph of reality, and it is compatible with many different quantum replacements. When we say curvature diverges, we are describing what the equations do as they are pushed toward regimes they were never experimentally certified to handle. We are not claiming we have measured an infinity, and we are not claiming the universe contains actual mathematical divergences. The honest stance is conditional, and the documentary should keep that conditionality in view. If general relativity remains valid arbitrarily deep, then a singularity forms, and the classical story ends in incompleteness. If quantum gravity intervenes at Planck curvature, then the singularity is replaced, and the replacement could be a bounce, a fuzzball, or something we cannot yet name. The replacement might even alter what we mean by inside, because the classical inside is defined by causal structure that quantum effects may modify. This uncertainty is not a failure of science, and it is not an invitation to mysticism. It is the frontier line where science marks what is known, what is inferred, and what is missing, and where the next generation of ideas must earn their place. The documentary's hook returns here with sharper meaning, anchored in a real sky and a real gravitational pull. Somewhere in the Milky Way, an invisible object rules stellar orbits with clean precision, and the choreography of those stars traces a mass too compact to be anything else. Its exterior is almost boringly consistent with Einstein, and that boredom is a triumph of prediction. Yet the same equations insist that inside the description runs into a wall, and the wall is not made of matter but of conceptual failure. We can now state the chapter's core claim in one breath, and it lands like a verdict. The centre of a black hole is where our best theory predicts its own breakdown, and where the next theory must do more than decorate the old one. From here, the journey cannot be only about falling inward, because the inward path is sealed from our instruments. It must also be about what the universe allows to be remembered, because memory in physics is information, and information is what quantum theory refuses to erase, because the mystery of the centre is inseparable from the mystery of information. What does a black hole do to the past that falls in? Does it hide it, transform it, or return it in a form we have not yet learned to read? Next, we follow that question to its sharpest edge, where principles collide and compromises feel expensive. If the universe is quantum, then the horizon and the singularity must be rewritten together, and the rewrite will tell us what space-time really means. We have followed gravity to the horizon and theory toward the centre. Now the journey becomes bookkeeping, what the universe is allowed to forget. Classical relativity makes a clean promise from the outside, and it sounds almost like a law of nature. Whatever crosses the horizon cannot send a message back out. That promise is not only about light, rockets, or courage under pressure. It is about causal structure, about which events can influence which futures. In space-time diagrams, the horizon is drawn as a boundary of light cones. Inside it, every future-directed path points deeper inward, even if you fire engines outward. From far away, that boundary looks crisp and geometric, like a circle cut into darkness. The black hole appears to be a one-way surface, an accounting line that nothing can cross twice. Quantum mechanics makes a different promise, equally strict and equally non-negotiable. The full state evolves reversibly, and information is not erased. In technical language, time evolution is unitary, which means probabilities add up, and the wave function never loses its fine-grained structure. In plain language, nature keeps the ledger, even when we cannot read it. The tension is not philosophical decoration, and it is not a word game about definitions. It is a direct clash between our best theory of space-time and our best theory of matter. To see the clash, we start with a quiet quantum fact that becomes loud near horizons. Empty space is not empty, because fields fluctuate even in vacuum. These are not particles popping in and out in the cartoon sense, but unavoidable quantum uncertainties in field amplitudes. Even the lowest energy state has jitter, like a violin string that cannot be perfectly still. Near a horizon, those fluctuations are distorted by curvature, and by the separation of inside from outside. Modes that would normally pair up are split. A useful way to picture it is to imagine wave modes stretched across the horizon, then torn into two descriptions. One part is accessible to distant observers, and the other part is trapped behind causal walls. In a simplified picture, excitations appear in correlated pairs near the horizon. One partner escapes outward, and one partner falls inward. The pairing is not optional, because it is rooted in entanglement, the quantum link that makes outcomes correlated even when separated. The horizon forces us to trace over what we cannot access, and that tracing changes what we predict. Energy conservation is saved by the geometry's accounting, although the bookkeeping looks strange at first. The escaping partner carries positive energy to infinity, and the infalling partner effectively carries negative energy into the whole. Negative energy here is not a new exotic substance floating around the universe. It is energy defined relative to infinity, and the curved space-time near the horizon allows that relative sign in the local balance. The result is Hawking radiation, and it is thermal to an excellent approximation. A black hole behaves like a hot object with a temperature set by its gravity. The temperature depends on surface gravity, which is essentially how hard the horizon pulls on nearby light rays. Increase the mass, and the horizon's pull becomes gentler per unit area, so the temperature drops. Visually, we can imagine the horizon as a dark sphere with a faint ghostly shimmer. The glow is not a flame but a quantum leak, a slow drizzle of quanta emerging from curvature. That temperature is tiny for astrophysical black holes, and it is easy to underestimate just how tiny. For a solar mass black hole, it is far below the cosmic microwave background, so it absorbs more than it emits today. The cosmic microwave background is a bath at about 2.7 Kelvin, a leftover afterglow from the early universe. Against that warm fog, a stellar black hole is colder than space itself, so it gains mass on balance. But the sign matters more than the size, because the direction of the arrow is set. If the universe cools enough, or if the hole is small enough, emission dominates and mass decreases. For small black holes, the temperature rises as the mass falls and the evaporation accelerates. The end is a runaway, a final brightening in the equations, although the details likely require quantum gravity. Evaporation is slow beyond intuition, and the timescales dwarf human history. A stellar mass black hole would outlive stars, galaxies, and most familiar cosmic structures. Even the proton, if it decays at all, would likely be gone before such a black hole finishes evaporating. The universe would be thin, dark, and cold, with black holes as some of the last warm things. Yet the logic is relentless, because it is tied to conservation laws and horizon geometry. If radiation carries energy away, the horizon shrinks, and the black hole's lifetime is finite. Hawking's result also forces a new word into the story, and it changes the tone of the object. Black holes have entropy, and entropy counts how many microscopic states match the same macroscopic appearance. In everyday terms, entropy measures hidden detail, the number of ways to arrange the internal ingredients without changing what you can see from outside. A smooth cup of coffee hides countless molecular motions, and a black hole hides far more. Jacob Bekenstein argued that black holes must have entropy to protect the second law, and he did so before Hawking found the radiation. If you drop entropy into a black hole, the outside world cannot track it. The black hole must compensate with its own entropy, or thermodynamics would fail. The horizon becomes a thermodynamic object, not a mere boundary line. Historically, this was a radical claim, because horizons had been treated as coordinate artifacts in some contexts. Bekenstein insisted they behave like physical systems, with temperature-like and entropy-like properties. Hawking's calculation fixed the scale of that entropy, and it made the analogy exact. The entropy is proportional to the horizon area, not the interior volume. This is the Bekenstein-Hawking area law, and it is one of the strangest formulas in physics. It suggests that the number of internal states grows like surface area. The constant of proportionality is set by fundamental constants, Planck's constant, Newton's constant, and the speed of the light, so the area is measured in Planck units. Each tiny patch of area corresponds to a finite number of bits, as if spacetime has a pixel scale. Area scaling hints at a limit on information storage in spacetime, and it is not a gentle hint. It implies that the maximum information in a region may be encoded on its boundary. If you try to pack more information into a volume, gravity responds by forming a horizon, and the bookkeeping flips from volume to surface. The universe seems to enforce a bound like a cosmic compression algorithm. That hint becomes the holographic principle, a phrase that sounds like science fiction but emerged from hard thermodynamic logic. The bulk description may be redundant, and the fundamental degrees of freedom may live on a lower dimensional screen. A hologram is a flat sheet that reconstructs a three-dimensional image through interference patterns. In the gravitational version, the pattern is quantum entanglement, and the image is the geometry we experience. The horizon is the most dramatic screen we know. It is where classical causality cuts the world in two, and where quantum fields insist on fluctuations. Now, the paradox can be stated without mysticism, and it can be stated as a clean contradiction. Suppose matter falls in as a pure quantum state, with definite correlations. A pure state is not simple, but it is complete, containing all phase information and all entanglement relationships. It is the difference between a sealed book and a pile of loose, shuffled pages. If the black hole radiates thermally, the outgoing radiation looks like a mixed state. It looks like heat, not like a message. Thermal radiation is characterized by a temperature and a spectrum, but it forgets the details of what made it. When we describe it statistically, we are admitting we cannot reconstruct the original microstate from the macroscopic glow. If the black hole evaporates completely, the final state is just that thermal radiation. A pure state would have evolved into a mixed state. That violates unitarity, the rule that quantum evolution preserves information, and it is not a small bookkeeping error. It breaks the core structure of quantum theory, the structure that underwrites everything from atoms to semiconductors. One response is to accept information loss as real, and to treat black holes as exceptions. Hawking himself once argued that black holes might destroy information, forcing a modification of quantum mechanics. In that view, the horizon is not merely a boundary of communication, but a boundary of existence for correlations. The universe would allow true erasure, a kind of fundamental forgetting. But information loss has a cost that spreads beyond black holes, and the cost is conceptual as well as technical. It threatens energy conservation in subtle ways, and it undermines the predictability built into quantum theory. If pure states can become mixed without an environment, then quantum evolution is no longer reversible even in principle. The rules that let us run equations backward would fail, and the notion of a closed system would become ambiguous. Another response is to insist that information is not destroyed, only hidden. The black hole plus radiation together might remain pure even if parts look thermal. This is a familiar quantum move, because subsystems can look random when they are entangled with something else. A single qubit can look maximally mixed, even when the full 2-qubit state is perfectly known. That response immediately raises a sharper question, and it is the one that cuts deepest. If information returns, where was it stored, and how did it cross a boundary that forbids escape? This is where the center becomes more than a location, and more than a dramatic word. The deep issue is not the singularity's coordinates, but the path of correlations through space-time. We can frame the problem as a triangle of principles, each one supported by decades of evidence. Unitarity must hold, effective field theory must work outside the horizon, and the equivalence principle says the horizon is locally calm. Effective field theory is our workhorse approximation, the method that lets us compute low-energy physics without knowing the ultraviolet completion. It is the reason we can trust quantum fields in curved spacetime, at least until curvatures become extreme. The equivalence principle is the statement that freefall erases gravity locally, so a small laboratory cannot detect a gravitational field. For a large black hole, the horizon curvature can be gentle, so crossing it should feel uneventful. The paradox claims the triangle cannot close, and it does so with the cold logic of entanglement. Something has to give, and each proposed fix sacrifices a different intuition. Black hole complementarity was an early attempt to keep the peace, and it was shaped by the practical limits of observation. It says no single observer can witness a contradiction, because inside and outside descriptions cannot be compared. To a distant observer, information is absorbed and later re-emitted in the Hawking radiation, as if it were stored on or near the horizon. To an infalling observer, information passes smoothly through the horizon, with no sign of a barrier. The two stories seem inconsistent if combined, because they suggest duplication of quantum information. Complementarity says they are not jointly measurable, so physics remains consistent in practice. Complementarity also leans on a practical limit that feels almost like a cosmic sensor. Any attempt to verify duplication would require collecting Hawking radiation and then jumping in, which may be impossible within the available time. But quantum theory is not only about practical limits, and it does not forgive contradictions that are merely hard to test. It is about logical consistency, and entanglement makes the logic unforgiving. As the black hole radiates, early Hawking quanta are entangled with partners behind the horizon. Later quanta must also be entangled if the spectrum stays thermal. The thermal character is not just a vague resemblance, but a statement about correlations. If each outgoing quantum is nearly maximally entangled with an interior partner, then the outside radiation alone remains close to a mixed thermal state. Yet if information is to come out, late radiation must be correlated with early radiation. Entanglement cannot be freely shared because of monogamy constraints. Monogamy is the rule that a system maximally entangled with one partner cannot be equally entangled with another. It is a mathematical property of quantum states, and it turns the paradox into a corner with no easy exit. This is the engine of the firewall argument, and it runs on bookkeeping rather than speculation. If late quanta are entangled with early quanta to restore purity, they cannot also be entangled with interior partners. Breaking that near-horizon entanglement would mean the horizon is not calm. It would mean high-energy excitations at the horizon, a firewall that burns the infalling observer. In visual terms, the horizon stops being a silent line and becomes a bright ring, a shell of violence where quantum fields are excited. The calm crossing promised by relativity would be replaced by a sudden lethal boundary. Firewalls preserve unitarity and standard quantum rules, and they keep effective field theory honest far away. They sacrifice the equivalence principle at the horizon, turning the boundary into a physical drama. Many physicists resist that outcome, because the equivalence principle is the backbone of general relativity. If it fails at horizons, it fails in the most extreme and revealing place. Others resist because the horizon is not a special place locally in classical theory, and that ordinariness is part of the theory's elegance. A firewall would make it special in a way that seems tuned to save information. So the debate becomes a test of what we trust most, and it becomes a mirror held up to our assumptions. Is the horizon ordinary to a freely falling observer, or is it a quantum membrane with violent structure? Holography offers a different escape route, and it does so by changing what inside means. It says the bulk interior may be encoded in boundary degrees of freedom, so information never truly disappears behind a separate region. In this view, the horizon is not a vault door that locks information away from reality. It is a feature of an emergent description, like a coastline that depends on the map's resolution. The most concrete version is AD-CFT, a duality between a gravity theory and a bulk spacetime and a quantum field theory on its boundary. It was discovered in the late 1990s, building on earlier insights from string theory and black hole thermodynamics. In that duality, the boundary theory is manifestly unitary, because it is an ordinary quantum system with a standard Hamiltonian. If the bulk contains black holes, their formation and evaporation must also be unitary in the dual description. AD-CFT is not a direct model of our universe's cosmology, because our universe does not appear to have AD's boundary conditions. Yet it is a proof of concept that gravity can be holographic and information preserving. It reframes the horizon as an emergent feature of a deeper quantum system. The interior becomes encoded, like a file compressed into correlations spread across the boundary. The metaphor is imperfect, but the point is sharp. The information is not stored at a point, and it is not stored in a hidden box. It is stored non-locally in patterns that only make sense when you read the whole system. This does not automatically tell an infalling observer what they experience, and it does not hand us a simple picture of the interior. It tells us that the bookkeeping can work, even when geometry suggests loss. The next step is to connect bookkeeping to a measurable curve, something you can plot and argue about. Don Page argued that if evaporation is unitary, the radiation's entropy should rise and then fall. Early on, radiation looks thermal, and entanglement entropy increases, because the radiation is strongly entangled with what remains. After roughly half the black hole's entropy has been radiated, the trend must reverse. This turning point is the Page time, and it is not a minor detail. Past it, new radiation must carry information about what fell in, reducing the entropy of the remaining black hole. In other words, the radiation must stop being merely heat and start being a message, even if the message is encoded in subtle correlations. The spectrum can remain nearly thermal while the fine-grained state becomes informative. For decades, Hawking's semi-classical calculations seemed to give only rising entropy, as if the radiation never learned anything new. The Page curve looked like a demand without a mechanism. Recent progress came from a surprising tool, one that sounds abstract but produces concrete numbers. In gravitational path integrals, new saddle points called replica wormholes contribute to entropy calculations. These are not necessarily traversable tunnels you could fly through, and they are not added by hand as science fiction. They are configurations that appear when you compute entropies using the replica trick, a standard method for handling logarithms of density matrices. Those contributions lead to the island formula, and the phrase island is chosen carefully. The entropy of radiation is computed by allowing the entanglement wedge to include an island region inside the black hole. In that picture, part of the interior is effectively counted as belonging to the radiation's quantum state. The boundary between inside and outside shifts in the accounting. The shift is determined by a quantum extremization principle, balancing an area term against ordinary quantum entropy. The result is that the minimal bookkeeping surface can jump, and the ledger redraws its own borders. The result reproduces the page curve in controlled settings, where calculations can be done cleanly. Entropy rises early, then turns over, consistent with unitary evaporation. Islands do not show information riding out on obvious particles, like labels attached to photons. They show information emerging through subtle correlations that semi-classical reasoning missed. It is a reminder that thermal is often a coarse description, and coarse descriptions can hide structure. The radiation can look like noise while still carrying a recoverable pattern, like a scrambled signal that becomes clear only with the right key. This is progress, but it is not a final map, and the caution matters. The calculations are clearest in simplified models and in ADS-like settings, not in full astrophysical realism. Still, the message is sharp, and it changes what we dare to assume. The horizon may not be the ultimate separator of degrees of freedom, even if it remains a causal separator for signals. That distinction matters for our central question, because it separates communication from correlation. What do we actually know about crossing the horizon and heading toward the center? We know the exterior behaves like Kerr to high precision, from orbits, accretion signatures, and gravitational wave ringdowns. We know jets are launched outside and cannot report from within. We can watch hot gas swirl into a flattened disk, bright in X-rays and radio, and we can infer spin from the disk's inner edge. We can also measure the mass from stellar motions, as if the black hole were a dark sun. We know semi-classical quantum field theory predicts Hawking radiation, even if it is too faint to detect for large holes today. We know the aerial law ties entropy to the horizon. We do not yet know the microscopic carriers of that entropy in our universe, and that ignorance is the open wound. We do not yet know whether the horizon is smooth, structured, or replaced. The information paradox forces a new reading of the word center, and it shifts the mystery outward. The deepest truth may not be a point of infinite curvature, but a rule about how information is counted. If holography is right, the interior is not an independent volume full of hidden bits. It is an emergent organization of boundary correlations, with geometry as a derived language. Then the inside is not a separate warehouse of facts, but a way of speaking about entanglement patterns. The center becomes a concept, not a place you can point to on a map. If complementarity is right, the interior exists for the infeeler, yet the outside description remains complete. Reality becomes observer-dependent in a precise, constrained way. The dependence is not arbitrary, and it is not a license for contradiction. It is a claim that different descriptions can be mutually exclusive yet individually consistent, because no experiment can combine them into a single ledger. If firewalls are right, the horizon is a quantum scar where smooth spacetime fails. The center's mystery moves outward, from the singularity to the boundary. Then the black hole is not a quiet region with drama only at the end. The drama is immediate, and the horizon becomes the place where quantum information forces spacetime to break its own promise. If islands are right, the boundary between inside and outside is not fixed by classical geometry. It is set by quantum extremization, and it can jump as evaporation proceeds. Then the center is not where the bookkeeping ends, but where the bookkeeping becomes non-local. The interior can be partially owned by the radiation, even while classical light cones still point inward. Each framework tries to preserve something we cannot bear to lose, and each one exposes a weakness in our intuition. Unitarity, locality, causality, and the equivalence principle cannot all be held with equal strength. This is why black holes are not only astrophysical objects, and not only curiosities at the edge of observation. They are stress tests for the conceptual foundations of physics. The paradox also loops back to gravitational waves, which have become our newest sense. Ringdown tests confirm the exterior, yet they cannot certify the horizon's quantum nature or the interior's bookkeeping. Echo searches probe whether horizons are perfectly absorbing, or whether near-horizon structure reflects waves. So far the evidence favours classical absorption, but sensitivity is still growing. A future detection of deviations would not automatically pick a winner, but it would narrow the space of stories we tell. Even a null result is information, because it constrains how exotic the near-horizon region can be. So the observational story remains asymmetric, and that asymmetry is part of the mystery. We can weigh the monarch at the Milky Way's centre, and we can map its shadow, yet we cannot read its ledger directly. The ledger is where the drama lives. because it is where physics keeps its promises or breaks them. A black hole seems to erase the past, yet quantum theory insists the past is never deleted. At this point, the documentary's hook returns with a harder edge. Somewhere in the Milky Way, an invisible object rules stellar orbits with quiet precision, and it may also be guarding the universe's deepest accounting rule. The centre, in this chapter, is no longer a destination for a falling body. It is the place where spacetime meets quantum information, and where our definitions of inside and outside may be negotiable. We end with a step back out to the cosmos. Black holes are not only endpoints of collapse, they are engines of feedback that shape galaxies and star formation. They merge, they grow, and they seed structure across cosmic time, leaving behind ripples we can now detect across the universe. Whatever the final answer to information, it must fit the universe we observe. Next, we widen the frame to the role black holes play in history. The journey to the centre becomes a journey through the architecture of the universe itself. We began with a hidden ruler in the Milky Way, bending starlight and time in silence. We end with a boundary where our maps stop, and the universe keeps going, still expanding, still indifferent, still measurable. Black holes exist because gravity leaves fingerprints we can cross-check across methods and across wavelengths. Stellar orbits around Sagittarius A weigh a compact mass with no luminous alternative, traced night after night as bright points loop through infrared darkness. Those stars accelerate as they swing past pericenter, and their paths close like clockwork, an orbiting proof that the mass is concentrated within a tiny volume. X-ray binaries show inner disks at relativistic speeds, with spectra shaped by strong gravity and by Doppler boosting that brightens the approaching side. Their flickering timing features, repeating on millisecond scales, match the orbital periods expected near a few gravitational radii. Gravitational waves from mergers match general relativity's templates through inseparable, merger, and ringdown, as if spacetime itself were a resonant instrument. The Event Horizon Telescope constrains horizon's scale geometry through a shadow shaped by light capture, a dark depression carved out of glowing plasma by curved null paths. Within current tests, horizons behave like general relativity predicts, as causal one-way boundaries rather than physical surfaces. Time dilation and redshift explain why distant observers never see a clean crossing, because signals stretch and fade as they climb out. Infalling clocks still reach the horizon in finite proper time, with no local wall required and no sudden drama in their immediate frame. The equivalence principle still rules there, at least for large holes, where tidal forces can be gentle at the boundary. Jets and disk winds launch outside the horizon, so they reveal near-horizon plasma, not the interior, like smoke tracing the mouth of a cave. We can measure mass and spin, and those numbers organize almost everything we observe, from luminosity to variability to jet shape. Disk inner edges, iron lines, and timing link spin to the last stable orbits, because the innermost stable circular orbit moves inward as rotation increases. In X-ray spectra, the iron K-alpha line becomes broadened and skewed, its red wing dragged downward by gravitational redshift and transverse Doppler effects. Jet power tracks spin and magnetic flux, especially in magnetically arrested disks, where fields pile up until they choke the inflow and tap rotational energy. Precession and alignment hint at frame dragging, yet environments still complicate clean causal claims. Gas supply, turbulence, and viewing angle all leave their own signatures. Sagittarius A stays dim because its accretion is inefficient at radiating energy, despite sitting at the centre of a galaxy full of gas. Hot, tenuous flows keep ions hotter than electrons, and much energy escapes in turbulence and outflows instead of shining as light. The plasma is collision poor, so temperature equilibration is slow, and the electrons that radiate do not receive the full heat budget. Its rapid flares likely come from magnetic reconnection and synchrotron processes near the horizon, where field lines snap and reconfigure in an instant. On screen, the glow would brighten and twist, as polarization vectors pivot like compass needles in a storm. Those flares probe plasma physics on light-minute scales, even when the microphysics remains debated, because the variability timescale sets the size of the emitting region, so we can speak confidently about the exterior and cautiously about what lies within. General relativity predicts the interior continues smoothly past the horizon, until curvature grows extreme and the classical description loses traction. In Schwarzschild, the centre is reached in finite time, and the singularity is geodesic in completeness, a statement about broken paths, not a visible point. In Kerr, inner horizons and Cauchy horizons appear, yet mass inflation likely destroys the idealized extensions, as in falling radiation blue shifts and amplifies stresses. Even the mathematics hints at instability, as though the interior refuses to remain a clean analytic continuation. The singularity is not a photographed object, but a warning that the theory is incomplete, like a map that ends in a blank margin. We suspect classical geometry holds until quantum gravity becomes unavoidable near Planck curvature, where spacetime itself may have a granular or emergent character. We do not know what replaces the classical centre, or whether the question even survives once the notion of distance breaks down. Candidates include a quantum core, a fuzzball of microstates, a bounce to another region, or a regular high curvature phase, each preserving something and each sacrificing something. The information problem forces the centre and the horizon into one combined accounting, because quantum theory insists that evolution preserves information. Hawking radiation follows from quantum fields near horizons, even if it is undetectable for large holes today, and the effect emerges from entanglement across the boundary. If evaporation is unitary, information must reappear in correlations, not in obvious labels, and not as a simple message stamped on each photon. Islands and page curve results show a consistent ledger in controlled models, yet the astrophysical translation is unsettled because real black holes live in messy, dynamical environments. The question lingers: is the horizon merely a geometric boundary, or also a bookkeeping device for quantum degrees of freedom? We do not know whether horizons are perfectly smooth, subtly structured, or violently modified, and the distinction could be observationally thin. Current ringdowns favour Kerr absorption, and echo searches have not found decisive reflections, though sensitivity and systematics still limit the verdict. Future high signal-to-noise spectroscopy could overdetermine remnants by multiple modes, checking whether the frequencies lock together as general relativity demands. Any deviation would point to new boundary conditions, not just new parameters, because the late-time ringing is a direct probe of how spacetime responds. Black holes also reshape the universe outside them, through feedback across cosmic time, turning small-scale gravity into large-scale architecture. Supermassive black holes co-evolve with galaxies, linking bulge properties to central mass, a relationship discovered as surveys connected stellar velocity dispersion to black hole weight. Accretion and jets heat gas, drive winds, and regulate star formation in clusters, preventing cooling flows from turning entire cores into star factories. In images, you can see cavities in X-ray gas, bubbles blown by jets, like fingerprints pressed into a glowing atmosphere. Yet we still debate the first seeds from stellar remnants, direct collapse, or primordial channels, because quasars appear early, already massive, already bright. Next tools will decide which speculations become constraints and which disappear as measurement tightens into inevitability. Lisa will hear massive black hole mergers and extreme mass ratio in spirals, mapping spacetime with precision as a small object traces thousands of relativistic orbits. Expanded EHT arrays will sharpen horizon-scale imaging and polarization, tracking magnetic structure and variability, and turning static shadows into time-resolved movies. X-ray timing and polarimetry will test disk geometry, coronal physics, and strong field light bending, separating competing models with orientation and phase information. Multi-messenger campaigns will connect jets, disks, and gravitational waves into one causal story, so that a chirp, a flare, and a radio knot become linked chapters of the same event. This returns us to the central question, now answered in layers we can defend. We know what happens as you approach and cross the horizon, in the language of tested geometry and carefully checked signals. We can infer what likely happens deeper inside, until quantum gravity must take over, because the equations push us there with relentless consistency. We cannot yet say what the true centre is, because the centre is where our theories stop agreeing, and where words like place and time may stop behaving. The journey inward ends at the boundary of knowledge, and that boundary is the point, not a failure. The centre is a map edge, not a destination, and it forces cosmology to confront space, time, and information as physical things. When we stare at that edge, we are also staring at the limits of prediction, and at the hidden assumptions behind our most trusted laws, Across the cosmos are billions of black holes, each a silent experiment running for eons, each one a controlled extreme we cannot build. They are the universe's darkest objects and its most illuminating teachers, because they simplify the world down to mass, spin, and gravity. They invite us to listen harder, see sharper, and rethink what reality is, before the next observation redraws the boundary again. We began with darkness that has a shape, a gravity-made object we can weigh, map, and cross-check without ever seeing a surface. From Esagara's star-traced mass to the Event Horizon Telescope's shadow, from X-ray hot disks to polarized jets,